This first week is going to be an interesting one. We are actually going to be looking over a little bit of theory with Vex, also talking about times we might want to use it and ways in which we would want to use it. And then we're going to dive straight in to try and figure out the kind of basic foundations of the language itself. So it's going to be quite complicated trying to ramp up throughout this course. So feel free to look over these lessons over and over again until you get a solid understanding of them. There's a lot of information packed into these, but I'm hoping that this week we're actually going to be able to figure out a little bit as to how this language works, a little bit about how we might implement this, and ways in which we can kind of use our logical thinking to approach Vex and make it easier. So I'm going to be going over a couple of tips and tricks in this, but for the most part, I'm going to be showing you basic foundations of the language, conditionals, loops, parameters, and how all of these things come together. And then by the end of this week, we should have a basis for which we can understand future content, and we bring all of this knowledge together to make interesting, creative, problem-solving wrangles in Houdini. So I really hope you enjoy it. Thanks so much for being here on this journey, learning Vex, and hopefully by the end of this week, you should be feeling really good about knowing a brand new language. So thanks so much. Hope you enjoy it. So this is our first lesson in 8 weeks of learning about Vex. And in this week, we are just going to be learning about our basic concepts in the language. I'm going to be running through an introduction to the language. I'm going to be using Vex examples to show you exactly what the language is, why use the language, and when to use the language. So this is going to be a kind of mix of practical examples, the theory behind Vex and the language itself, as well as a little bit of philosophy from a computer science perspective as to how we should think when using something like Vex, and also the kind of underlying philosophies of why people use Vex in the first place. So it's going to be really interesting. We're going to have a great time learning more about this wonderful language. And so just to start off, I want to sort of define exactly what Vex is. So you're probably familiar with all of the concepts that exist within Houdini so far. If we were to put down a geometry node, you understand the contexts, you understand what a node is. So if I were to put down a box, which we'll be doing many times, you'll understand exactly what's going on here. You'll understand that there are points in space. You'll understand that these have positions in X, Y, and Z, all of these things. So without necessarily even realizing it, you might already have quite a foundational knowledge of computer graphics. This is really useful because everything we do in Vex is going to be related back to the same series of computer graphics concepts. And this essentially means that your knowledge about 3D space, what happens in 3D, and the idiosyncrasies of 3D are going to be perfect tethers into the way in which we define and let our knowledge sink in. So what exactly is Vex? Well, you may be aware of languages such as C and C++. You might not necessarily understand them, but you'll know that they make up what happens within our computer to a certain extent. Just to simplify things massively. So we have Houdini, a program that is built from the ground up in various languages such as C and C++. And as a result of a great deal of code and integration to our operating system, we have the ability to visualize 3D objects through this code. Vex is a language with similarities to these, but the context in which we view it is very, very, very small. Vex is a kernel expression language, which essentially means that we only see it within specific contexts within Houdini. So for example, if we were to put down an attribute wrangle, Vex only lives inside of this attribute wrangle. It does not go anywhere else. So it is a programming language which is essentially a set of instructions. You'll provide instructions one after the other inside of this language, and they do things within this context. So there are a couple of contexts for Vex in Houdini. There are geometry contexts where we will use Vex to alter, visualize geometry. There's Vex in chops, which we won't be going over in this course, but we'll be able to build some problem solving and some powers of deduction across the length of this course that will allow you to tackle unusual concepts and navigate problem solving in a way that allows you to sort of apply some lateral thought into the way we think about Vex, because we don't just want to have our knowledge live entirely inside of this small black box here. There is also the shading context for Vex, where if you are a little bit old school, you might be familiar with mantra shaders, camera shading, and the like. So once again, not something that we're necessarily going to delve into, as using Vex in mantra is a much more unusual use case in a modern professional environment. So what we're essentially doing here is using Vex in a way that only pertains to our geometry. Vex, as of itself, lives inside of here and is a set of instructions within Houdini. So when we write code in here, we will be providing instructions one after another and holding information within these instructions that allow us to perform various operations on surfaces, geometry, and pieces of data. Vex itself is described as a high-performance expression language in Houdini, used for writing shaders, controlling geometry, and it resembles C and C++ in syntax. What this essentially means is that the format in which we write Vex is also going to be similar to C and C++, although there is not much point in knowing either of these languages before we go into Vex, or really any other languages, because the ways in which Vex are made up syntactically are quite unique, in the sense that they're a combination of various languages, and also for the fact that you'll find that pretty quickly a lot of Vex is really about memorizing good functions to perform repetitive tasks. So when we're learning the language across the entirety of this course, we'll be picking up not only skills in programming, but we'll also be figuring out ways in which side effects have made learning the Vex language and utilizing it easy for us. Because if you were to start, say, programming your own software using C or C++, you'll find that without pulling in code from elsewhere, you are quite on your own. And you're definitely not on your own, and you're not at a very low level in Vex. You're always going to have functions that handle very complicated mathematical capabilities for you. Another thing about Vex is that it integrates very nicely with this node-based workflow. You can, of course, get contexts for Vex where, say, for example, you were to put down a point VOP. You may have seen this before. We go in here and we have a sort of visual programming. But you will find if you right click on here and you go to Vex VOP options, that this is actually always just code. So it was code all along. And when you're performing operations through nodes, you'll find that this in of itself is a sort of visual programming. So let's say, for example, we wanted to put a box and we wanted to transform it in space. If we were to move it upwards by 1 unit, we would find that this is a set of instructions in of itself. This is, first of all, we create our box, which we could do in Vex. And then we are moving it up by 1, which is something that we can also do in Vex. So just a little bit of thought for how we can kind of visualize a text-based set of instructions as opposed to a visual set of instructions, which is what we're getting from our visual programming through nodes here. So what are the reasons why we might want to use Vex? Well, first of all, we get a very good look at what exactly is happening within the context of a Houdini. When we start writing Vex code, we're performing functions and creating functionality that gets us much closer to the core of what is happening inside of Houdini than we would have through nodes. So in some ways, you can sort of think of Vex as almost like a teaching tool for understanding a little bit more about how computer graphics and things inside of Houdini work. And you can also think of it as a way to get very fine-grained functionality on a node. So if we wanted to create a script that did things randomly on a box, in the spirit of proceduralism, there are, say, functions that will randomize per point. various things without the need for doing a round trip of attributes and relaying, for loops, etc. We can keep all of that functionality in here and give it very unique and fine-grained differences between what we would get in nodes. It's also a very efficient way of performing these kinds of processes in Houdini. So you'll notice that now that we have our attribute wrangle down here, and this is the context for which we are going to be writing Vex within, you'll see here that we have a couple of parameters that exist here. The one that we're going to be changing the most is this run over parameter. And you can actually see here, it says here, apply the Vex code to each component of this type, points, primitive faces, or vertices, or choose detail to run the code only once. For each component, the code runs with the attributes bound to the variables, starting with for example, @cd for reading and writing. So what we're essentially doing here is we're taking our set of instructions, and let's say, for example, we had a for each loop that we're looking at through our tab menu here. We say for each point. Every time we loop through this block, we are looking at an individual point. I'll just make this bigger so you can see what's going on here. So we have our box and then the point that we're looping through. And when we come out the other side, we've got all of our points. We've done something to these points. If I were to put a color down and give each point a color, let's say I wanted to color each point red, we would come through the other end and find that we had looped through our box and colored each individual point within our box red. The same can be said here for what is going on in this run over parameter in our attribute wrangle. Our run over parameter is essentially saying, look at each individual point. So if I were to type in a piece of code in here, that piece of code would be applied to every single one of the points at which we were running over. So this is another reason why you can sort of think as Vex, especially in the context of geometry, as a kernel language. While we can create code that will run over every point, and we can collect every point individually using code, by default, the creators of Houdini side effects have sort of deemed it that the likeliest outcome for what we are going to be doing with Vex is going to be running over a geometry type. So when it says run over points, every time we run an instruction in here, it is going to be running over every point individually. And the same would be said for if we were in primitive mode, vert mode, and numbers in detail, we don't really need to think about very much right now. And the same can be said for our for each loop. If we wanted to iterate over each piece, we can iterate over primitives. So we can color each primitive instead of points. We can perform these same types of functions in nodes. But the reason why we would want to do it in Vex is simply because we have that incredibly fine-grained and dynamic control, which still is in the same vein, in the spirit of proceduralism that Houdini affords to us. So just to recap, why we're using Vex, we get a significant amount of control, but we also get a significant amount of efficiency through using this. It isn't necessarily the case that for every time you'll write code in here, it will be more efficient than its node counterpart, just because of the tricky nature of making something that compiles at the time at which it's written and run instantly and efficiently. But you'll find that a lot of the time you can write code in the context of Vex. And because we are running over every point individually in this kernel, we will find that our processes are threaded across the CPU. So for every couple of thousand points we have, these points will be run over on the CPU, and each instruction that we write in here will be split out across all of our points and split across all of our threads on our computer. So with that added efficiency, we can create code that is very, very performant and very fast. It is almost exclusively executed on the CPU. But even within this, it can run incredibly quickly. We can, say, for example, have a point cloud with millions of points, and the more points we add, the more efficient this is going to be because of the nature of how threading is handled in an attribute wrangle. The last reason as to why we would want to use Vex instead of, say, something like writing our own plugin in C++ or doing something very difficult is because it's integrated in a way that's designed to be fast. It might seem unintuitive initially, especially if you're coming from a background where you haven't explored programming before. It might seem unintuitive that programming and writing code can be fast, but you'll begin to see soon as to why I say that. It's quite often that you'll find yourself looking for functionality that's described in a node, and you'll find yourself looking for a couple of nodes that work with one another in such a way that is actually quite complicated to describe in the context of having nodes. For example, the ray SOP. If we wanted to ray hundreds of objects, we would have to put it in a for loop. And if we wanted these pieces that we were raying, say for example, we wanted to ray every single primitive individually on this box to a pig head, for example, the level of interactability that we have between those primitives is quite limited. What we can do with something like an attribute wrangle is not only hook up all of these inputs and have code run in a variety of geometries as well as contexts, we can begin to implement an interactability where we don't need to add nodes or do some additional planning around our node graph in order to account for different levels and layers of functionality that we want to add to something. So this makes Vex perfect for prototyping tools, prototyping shaders, and prototyping things that are conceptually very difficult to do in other languages and in other styles. If you've come from a background where you have written shaders before, you'll be familiar with this kind of concept where you're trying to write things in a way that is fast, efficient, and easily understandable by people seeing this. And it's only after learning the basics of Vex and learning the kind of workflows that you'll want to adopt when using Vex that you'll begin to see how this is possible. You'll also find that quite often Vex is used in a way that is sort of independent of any other functionality like other programming languages are. So you'll find that, for example, pipeline tools and UIs are quite often written inside of Python. This is just going to demonstrate the kinds of differences between the two languages. You'll have something written with the explicit purpose of being user-friendly in Python. But with Vex, because it's conditioned entirely within our attribute wrangle, we have to go a slightly greater length in order to make this user-friendly. So, for example, we have this button up here, which allows us to create spare parameters for unique calls of ch. And that might seem a little bit overwhelming now, but I promise you it won't be. But what the point here is essentially is that the attribute wrangle in of itself is a sort of development environment designed with the idea of having appended Houdini functionality to Vex rather than the other way around. If you're looking to create a UI for a tool, for example, Vex is not the place that we're going to want to do this. If you want to create something that saves files to disk, that isn't possible inside of Vex because it's contained inside of here. But the kinds of things that we are going to want to do inside of here are fast and efficient geometry operations, reading parameters, and iterating over hundreds, thousands, or millions of points with a high degree of efficiency. A really good use case for Vex, for example, is the movie Interstellar. You might have seen a large amount of press given to the black hole that was created. You might be surprised to know that parts of this black hole simulation were actually R&D'd using Houdini, Vex, and Mantra. The reason for this is that because it's actually quite an incredible thing that we have this language inside of Houdini. It allows us to take concepts such as rendering, such as editing geometry, and such as shader creation that would traditionally be locked off for most developers because it would require you to install some kind of rendering engine or append the code for rendering, import packages such as Vulkan, set those up, and create links between your code and those rendering engines. And that in of itself takes a lot of learning, a lot of technical literacy, and can be incredibly difficult to just get over that one hurdle before we start prototyping what's going on in here. But the good thing is that because we already understand Houdini to a certain degree, hopefully, we'll be able to apply concepts that we know within Houdini into Vex and begin prototyping within this context very, very quickly. So I'm going to start off this week just introducing concepts to you, and we will progressively get more abstract over time with our implementations. And I'm hoping that by the end of this course, you'll not only be able to write code, which is obviously the most important thing to start out, is to understand the syntax and write code and understand how we collate these instructions in a way that is meaningful. But you'll also be able to approach new tasks, which is at the core of the Houdini artist's toolset. It's about problem solving, it's about approaching new tasks, and it's also about being able to get a little bit creative with code, which people might quite often think isn't necessarily all that possible. But I'm going to make it my mission to show you that you can have fun, be creative, and be very fast in your iterative process when using something like Vex. So stick with me for part 2, where I'm going to be describing how to create your variables and how to relate them back to attributes. And we're going to write our first lines of code in a way that gives us an opportunity to explore the relationship between Houdini and Vex and hopefully kickstart your learning experience. So thanks so much. I'll see you next time. Hey everyone, welcome back. So now we're actually going to be writing our first piece of code. So the first thing that we need to actually run through is how this language is constructed. Learning a programming language, if you've not done it before, is a little bit like learning a new language. There are rules and systems in place that have been constructed over time to make things easier and more sensible when running through something. So, for example, in a programming language, rules will be set up based around the limitations of what you're doing and also to kind of make a level of equality when you are working with other people. So, for example, readability is quite an important thing in Vex. So just in the same way that you're learning a new language, we're also going to be learning the rules and capabilities of those rules within the language. So the easiest way for me to show you how this works is to just go and create our geometry node, put down a box again, and then just put down an attribute wrangle. So we covered the attribute wrangle a little bit in the last lesson, and you probably already know at least a small amount about what this does. You can hook this up to any geometry node of any kind, and it will run over exactly what it says here. And we learned that last time as well. If you middle mouse on here, you'll see exactly how many things it's going to run over. So if we're running over points, it's going to be 8 points we run over, prims, 6 prims, verse 24. So we put that in here. And that is the kind of first limitation of what we're doing within an attribute wrangle. You can jump straight in to using another context. Say, for example, you type in primitive wrangle, or you can type in vertex wrangle. And the name will be in accordance of the one that you put down, but the nature of the node will be the same. It will still be an attribute wrangle SOP, running over primitives, running over vertices. The only thing that's changed between these is the condition at which it is running over. So these attribute wrangles in SOPs primarily run over geometry. And if we were to look at the other types of wrangles, you can see at this point in time, there are deformation wrangles, volume wrangles, height field wrangles, rig attribute wrangles. So many different contexts for all of these. This is just one of the rules that we kind of have when working with Vex. The documentation does a really good job of explaining how many contexts there are. So feel free to look at the Vex language reference page on the side of Vex documentation. But for the purposes of learning the language itself, we're just going to be using this geometry context. So how exactly does our instruction work when we're writing in this language? Well, the first thing you're usually going to start with doing is creating a variable of some kind. These are going to be comprised of various data types. If we were to start typing our first piece of code, we might begin by creating an integer. And an integer is just a number that looks like this with no decimal counterpart afterwards. So it could be 1, 2, 11, 111. It could be any amount of numbers with no decimal afterwards. The way that we would define a integer inside of Vex is not by just typing in the number, because we need to be able to reference it after the fact. So we need to give this number a name. So let's say, for example, we had the number 99. The first thing we need to do is tell this that this is going to have a name. The correct way of doing this is to say example equals 99. You still notice that we've got our attribute wrangle error here. And this is a good example of one of the ways in which we can use the wrangle to kind of teach us a little bit more as well about the way in which we're supposed to be writing code. So it says here, syntax error, expected a curly bracket, expected a semicolon. So what exactly does this mean? This basically means that we've missed off this at the end. This is the end of an instruction. This is the end of a piece of code that we have told Vex to perform inside of this wrangle. And then we check back and we've still got our error. So we fixed these first two problems using the errors that the wrangle gives us. Reference to undefined variable example. So one thing that makes Vex quite similar to C and C++, if you've ever seen something of the like before, is that we actually have to tell Vex that this is an integer. This isn't something that we have to do in Python, for example, but it is something that we have to do in Vex. The way in which we'll do this is that we have our variable name here. We're using this equal sign here to say that the named variable example is going to be the integer 99, and we're closing this instruction with this colon here. What we need to do is say that this is actually an integer before we have written in an integer. The way that we do it is by typing int. Integer example equals 99 semicolon. So this is already quite a bit to unpack. The best way to understand this is to once again come back to the idea that we are looking at this as a set of instructions. We're creating a named number 99 as our first bit of code. And we are saying this is an integer, has no decimal place or fractional value. In Vex language and in programming in general, you'll see the decimal position after the number referred to as a fractional. And the name of this variable, so the name of the 99 is example. And this named integer example is equal to 99. If you've already approached this from Python or you've already done a little bit of Vex code, you may already find this quite easy to understand. But for the people who haven't, don't worry if this is quite a tough thing to take in, because these first steps are going to be the hardest. The first hurdles to learning a programming language is to understand first that this is an instructional kernel language that sits within the context of our wrangle. So to understand that this code is running over every single one of the 8 points in our cube. And then we are creating and separating instructions by this semicolon and telling Vex what these instructions are. So we've created example. This is our integer 99. We can explore some other commonly found data types in Vex. For example, we could say float example equals 99.99. Immediately, we are going to get an error. What is happening here? Well, first of all, we have written in this example variable twice. Some languages, you're allowed to do this. For defined types, it is very rare to see a language that would allow this. But if we look here, multiple declarations of variable example. So another reason as to why you can lean on the attribute wrangle to tell you exactly what you're doing wrong. So, couple of rules that we've already learned. We need to separate each instruction by a semicolon. When we want a piece of data that we want to access later, we need to give it a name, and we need to say exactly what this form is going to take. And the rule that we've just learned here is that we can't make this example twice. So I'm just going to do it like this, and this removes the error. The float denotes that this will have a fractional value, and this can be as many decimal places as we want it to be. This floating point basically just means that there will be a fractional value after this. So even if we were to type in 99, it would still have a fractional value afterwards as close to 99.0 as it could possibly get. Without going too much into the kind of theory as to the difference between floats and integers, The difference can really be summed up in the idea that computers find it very hard to get an integer level of accuracy in a float. So you might find that, for example, a number quite often ends up looking like this. So that is the reason why we would use an integer instead of a float in certain cases. So we have our float example 99.99. But if we wanted both our integer and our float, we could say, for example, integer example A is equal to 99 and float example B is equal to 99.99. This is fine in the context of an attribute wrangle because we have defined two different variables. So these are two different accessible pieces of memory that we can have a look at and recall in the future. This example A here is the integer 99, and this example B here is the floating point number 99.99. And these can share the same value as well. And we can cast them the same. The only difference being is that this will be the integer data type. This will be the float point data type. Say 99.99. But how does Vex know the difference between letters and numbers? Well, the next thing that we can take a look at is actually how we get text into Vex. What text is commonly known as when we create it as a data type in programming is a string. So we would set type in string, here, like this, to denote that what we're about to type is text. And we could say example C is equal to, we could just say hello world and close that with a semicolon. But we have our next rule here, which is that even though it says here expecting a semicolon, this is not a problem that can be fixed by writing in a semicolon. What's going on here is that it can't tell the difference between what we're doing over here and what we're doing here. It looks like we're trying to do something else. We need to say that this is actually a piece of data that is just text, and we would enclose this in quotation marks. This tells the programming language that this is a piece of text data that can be recalled later, and the string here is what this is over here. So when we assign text like this, this is the name of our variable, and this is the text that is held within our variable. In computer science, each one of these letters is an entry in a list of letters. So each letter is returned to us as a component of this overall data structure. For example, our first entry in the string is H, then E, then L, then L, then O. So this is just a way of representing in code a piece of text. There are more complicated data types that sort of represent this kind of idea that we have a series of entries into a variable such as vectors, which you may be familiar with already in CG, which can be denoted by saying vector. So vector example D equals. But how are we going to tell this that we need multiple numbers to be added in here? We will be exploring lists and arrays later on in this, as they are quite a tricky topic to handle. But just follow with me here, just so that we get an understanding of how exactly we're writing these things in. So we can define a vector as 3 floats. So all we need to do is enter in 3 floats in here. We can say with this curly brace notation, so we have our 2 curly braces and then this semicolon here. Our vector is 1, 1, 1. We have to separate each one of the component entries by a comma. And so if I get rid of everything else here and I just rename this to example, our vector variable example is 1, 1, 1. Same kind of idea as the string. We have 3 entries into this variable example. We have the component 1, the component 1, and the component 1. And if you're familiar with visualizing these kinds of vectors in 3D space, you might know this is a representation of a trail or a direction or a position in space. And one good reference for exactly what's going on with these data types is the geometry spreadsheet. You may realize that here we've got px, py, pz, and it's got this strange kind of notation here. We can access individual components and create new variables in the same way that it looks like in the geometry spreadsheet. If we want to, say, for example, make a new float called example x, which would be the x, the first component of our vector. So if we imagine we've got 0.5, minus 0.5, and then 0.5 up here, and we can actually put that into our top vector. So say 0.5 minus 0.5, and then another 0.5. We can say that our example x is actually example dot x. The reason for this is that because our vector is made up of 3 components, SideFX has already provided to us this handy syntax for being able to access an individual component of our vector in the same way that we look at it up here. So we have our px, our py, and pz, and p is essentially just a variable vector that has been named p for position in world space. And you probably will have accessed this geometry spreadsheet before. You know, you can access any node's attributes through this, and we can see here that we have 1 point attribute, which is our position. We'll see here that it says 3 float. So now we're starting to build an understanding and an idea of the kind of underlying forces in Houdini and the ways in which data are represented through a CG kind of format. We have the P position, that's a 3 float, and we've just typed in 3 floats in here to make up the basis of our vector example. And in order to get a singular component baked into a variable, example x, we can just write in the name of our example. We could also rename this to a component x just to make it a little bit more apparent that these aren't the same thing. So we've got our vector example, which is 3 floats here, and then our float component x, which is now equal to example.x. So instead of having to type in 0.5, because we can see here that this is 0.5 up here, we can make this a little bit more dynamic in the sense that we don't have to type in the number manually that we see up here as 0.5. We can just say that the first component of this vector example. So we just say example.x, and that tells us the first component, this x over here, would be 0.5 without us having to do anything. We could also do the same for y, and we could do the same for z. Other data types that exist in Vex will be the kind of more idiosyncratic data types, such as vector2, which is the same thing, but written with 2 floats instead of 3. Just kind of denoted by the name vector2, you can kind of get an idea of how exactly this works. So we miss off that extra 0.5, and if we write the wrong amount in here, we can see that it's quite strictly enforced that we need to have 2 floats in a vector2. So we just go down here and it says invalid array literal for type vector2. This is basically just telling us that we have inputted the wrong kind of data into this command up here. So we need to take it back, get rid of the 3rd entry, and we will be in a happy place again. Same thing for the type vector4, but we notice here that it actually works. Why does this work? Well, because in one, we were trying to fit 3 floats where 2 would fit. But in this, when we only provide 2 floats, it just gives us a value of 0 and 0 after the fact. So if we were to try to add another one, we would get the same error again. So we can underfit, but we can't overfit. These strictly enforced types are part of the reason why this type definition is so easy to read. Once you get your feet off the ground with a little bit more code practice, you'll be able to read variables as they are constructed inside of an attribute wrangle and get a better understanding of exactly what people are defining and what people are creating as their sort of instructions here in the attribute wrangle. We have data types such as a matrix, but this is quite complicated for what we're doing right now. You may know what a matrix is. It's just essentially the same thing as a vector, but slightly more dimensional in the way that it's used. It is going to be, for example, for a matrix 3, it is going to be 9 components instead of 3. Something that you can look up on the Vex language reference if you want to, but not imperative for our early stages of learning so far. We will get around in later lessons on how to use matrices and how to perform transformations with them. You may notice a kind of pre-existing matrix if you're familiar with them in the form of a transform. You can see our translate 3 components, rotate 3 components, scale 3 components. So they're just useful representations in nodes that come through and help define your knowledge of exactly what's going on in Vex. You'll notice as well that we don't actually have to do anything to execute our code. If we type in float example equals 0.1, this is actually taking time to run the code. As we see down here, our cook is 0.03 milliseconds. We don't have to do what we might do in a main loop in Python, where we have to explicitly state a set of parameters in which the code should run, because we already have a environment inside of Houdini that does all of this for us. So one benefit of using attribute wrangles in Houdini as opposed to using a script outside of Houdini is that the amount of setup time is almost zero. The chances that you'll have a technical issue in Houdini and the setup of your attribute wrangle is the reason as to why something isn't working is going to be very, very rare. Even in cases later on when we're looking at importing multiple objects into your attribute wrangle, the syntax for accessing this is very, very simple and is all designed in a way that can be fast, efficient, and work with your node-based workflow in a way that's intuitive and easy to understand from a visual perspective when you are putting a node graph together. So really useful stuff, really useful stuff. What we want to do to kind of see as to whether or not we're actually doing anything in our wrangle is explore the idea of how variables and attributes are actually very similar in their nature. And we're going to do this by creating our first variable attribute. So what we're going to do here is we're going to first just talk a little bit more about types in the context of attributes. And I'm going to show you how to mix and match the code between creating a variable and creating an attribute. So you'll notice here that we've got our 3float p position. And if I were to put down an attribute create, you're probably going to be familiar with attributes if you're doing this lesson. But if not, just follow with me and I'll do a bit of explaining as to how this works. And you'll see here that we've got class point, which is very similar actually to our attribute wrangle, running over points. We've got our type float. So we've got all of our different types that we've talked about. We've got a level of precision, which we don't really need to explore in this because we just auto just does all of this for us. And we've got our name of our attribute, which is similar to the way in which we create our variable. So we can see here now we've created ourselves attribute 1. We've got 4 entries down here in our attribute create. But we now know that because we're using a float, which is just a 1 fractional number, or a number with a fractional, we know that we're only going to need this one. So our default and our value writes this value to our node. So I'm just going to call this example. And we'll see here that we've created all of this with a value of 1.1. If we were to do the same for 1, we would see that we get 1.0 because we are using a float. If we do the same for integer, we get the number 1. And if we were to write a string, we could type 1, but this would be a actual character, or we could type in the actual characters of 1. But if we were to try to do the same thing in here, it would freak out and not let us do it. So what we can kind of glean from this is how exactly Vex is also going to treat our data types as we use them. If I were to go into integer here and say that the value that I want these ones to be at is 1.531, it would actually round it up to 2. So every time you use an integer in Vex, it's going to do the same thing. If we were to type in int example equals 1.53, we would get this kind of warning here saying implicit cast from float to int, use explicit cast instead. And whilst this warning sounds quite imposing, it's not actually affecting the outcome of our code, which is why it's just a warning. So it's just telling us that it's rounding this integer up, and it's warning us that because we've typed this so explicitly, it's warning us that the outcome of this isn't going to be 1.53. So the reason why it wants us to use an explicit class instead is because it wants to be happy in knowing that we've actually typed this out as we intended it when we created our integer variable. So variables and attributes. You'll notice here that if I call this foo, there's no attribute in here. How are we going to create an attribute in Vex in the same way that we did in our attribute create? Well, the easiest way to do it is to rely on our running over. So we're running over points, and using an easy bit of syntax with the @ symbol, we can automatically create a point attribute. The same would apply if we were on primitives or points or vertices. We're just going to stay on points for now. And if I were to say @foo equals foo, we would see here we've created a attribute. There's a big problem with this, and you may have spotted it straight away. This is an integer variable of 2. So why is it that here we've got 2.0? The reason for this is because whilst we have a very friendly syntax here for creating a attribute using the @ symbol instead of just typing in foo equals foo, we'd say @foo equals foo. This is creating a float for us. So the real syntax we need to be aware of when creating an attribute isn't just that we can type in, for example, @foo equals 2, because even if we say that this is specifically an integer by writing only a 2, it's not respecting this because it has no idea what kind of attribute we're trying to create by default. So what we need to do here is, in the same way that we've typed in foo, we need to do the attribute equivalent of that. So the correct syntax for creating an integer attribute in an attribute wrangle is to say I for integer @foo. And this is another thing that's also explored a little bit in the Vex language reference, if you want to just recap on what it says here in a kind of text format. And what this essentially means now is that we are casting and creating an attribute in the same way that we may do a variable. And in the same way that we could access foo, if we had int foo equals 2, we could say our attribute is now 2. Our attribute is not equal to foo in the geometry spreadsheet because foo is just a representation of a piece of data that is assigned with the value of 2. So foo is 2, and now foo is foo. And just to put it in kind of more plain terms, we have an instruction here that creates a reference to the number 2 with the name of foo. We then create an attribute with any name we want after the @ sign. So we could say @example. I, integer, create an attribute, example, is now equal to this number 2, which is defined by the reference from foo. And as a result of all of this, we now have an attribute given to us on our box with the value of 2. The same applies for creating a float. Even though we create a float by default, we would just say here f@example equals foo. And the same for a string. If we were to create string foo equals hello world, we would say s @bar equals foo. And we see here we now have a string text attribute, and it says here we have one unique entry, which is a nice way for Houdini to wrap up the idea that we can have a certain amount of unique values in an attribute. We have one unique value shared across all points that have the string value of hello world. We also don't even necessarily have to create a value for our variable. We can create an instruction that says just create the reference with no value attached to it. We can say float foo and then end it there with our semicolon at the end of the line. And I've just assigned it from float to string, which is not possible. So we just want to make sure that we've got the right value in here and just say f@bar. So I'll just get rid of this again and just say f@bar equals foo. And we can see here that even though we have a warning here using an uninitialized variable, we have a value of 0 in here. So we can create an uninitialized reference to a float, which by default takes the value of 0.0. Same for an integer. So we would say 0 is represented through the uninitialized variable here. The same for if we wanted to create our vector again, So vector example equals 0.5 minus 0.5 and 0.5. If we were to say f to denote a float, at for an attribute, and bar is the name of our attribute, is equal to example x. We don't get any qualms here because we're not trying to cast a vector to a float. We are just saying that the floating point first component of x out of x, y, and z from the vector is now our float 0.5 bar attribute over here. So interesting stuff. A nice, easily readable language that kind of gives us the tools to create references to data as and when we need them in a quite descriptive way. Some languages can be quite difficult to learn in the sense that having an undefined series of types means you have to understand more about the types than you do about the language. But Vex is nice in the sense that you can say vector and people will see that at the start of a line and they'll immediately know you are probably doing one of a few things in relation to what your code is doing here. So if someone sees you're doing stuff with strings, they might immediately assume you're doing something with group names or names of attributes, etc. If someone sees you're doing something with a vector, they might think you're trying to make a force or a vector trail or some kind of positional geometry change. So just try and wrap your head around the idea that these various data types that we've explored so far, and please go over them again and again if you feel like you need to in order to kind of understand them a little bit more. But try to wrap your head around the idea that these data types all take their own forms in unique ways inside of Vex, and they have representations through the data in which we are trying to understand in here. One last thing I want to show you as well is that we can just create a vector attribute as well. If we just say v at bar equals example. So generally, the more standard types will just be the first letter of what they are, and then the at symbol to denote this is an attribute, and then the name of the attribute as part of that. So we've created a pretty reasonably useful command here, or set of commands. We've created a number that we want to have a reference to in our script, and we have also created an attribute that shares the value of this reference to a variable. And we'll see up here as well that this has been cast equally across all points. And if we were to do this to say primitives, and we just go over here to the primitives tab of the geometry spreadsheet, we'll see that every primitive now has the x, y, and z values of the attribute bar with this same value. So we see down here, if we middle mouse on this as well, we now have a primitive attribute that is a 3-float bar. So it's not limited to the types of geometry you're trying to put this on. Points, vertices, it will change depending on what you are running over. And running over is probably as simple as it could probably be explained in the context of an attribute wrangle. So I hope you learned something new from all of this. This is some interesting stuff. And if you found this quite easy and you want a little bit more of a challenge, go to the Vex language reference and maybe see if you can create your own data type by using a user-defined struct. Cool thing that's quite unusual to see in Vex, but just a nice way to really solidify your knowledge of variables and attributes. So I hope you enjoyed being able to write your own attributes in the same way that you might use in an attribute create. And I'll see you next time for when we learn a little bit more about functions and how we can create some more complex instructionals to tell Vex exactly what kind of mathematical operations we want to do and how we can wrap up instructions in a way that doesn't require us to write repetitive code-based tasks in a wrangle. So thanks so much, and I'll see you next time. So we understand now a little bit about the way that these work. This is a set of instructions that we are providing to our attribute wrangle. We know that we're running over points because this input geometry is connected up to the first input of our attribute wrangle. And this example here is 3 floats defined by a set of curly braces, 3 numbers separated by a comma, and then this instruction is capped off at the end by a semicolon. We tell Vex that this is going to be a vector, which means it's going to be 3 floats, and we give it the name example as a reference to be used in the future. Down here, we say that a vector attribute has been created called bar, and we are telling it that the value of bar should be referenced by the variable up here named example. All of this is good, but what if we want to create some more advanced complex functionality? And what if we want to sort of abstract away this extra complexity in a way that is repetitive and that we can reuse without having to type massive amounts of code every time we want to do something complex? So that's where functions come in. Before we take a look at functions, I just want to briefly go over some of the mathematical operations we can do within Vex, just to make it easier for people to understand when you see these kinds of things. So if I just start from the beginning here again, and I say float foo equals 0.1, I'm very quickly just going to create a second float called bar, and we give that maybe 0.2. And I'm just going to create a float attribute by saying f at example equals foo. So you can see here, we've got two variables in here called foo and bar. And the only reference passed in here is foo, which means it's 0.1. Let's say, for example, we want to add these up really quickly. We can say foo plus bar, which would give us 0.3. That's 0.1 and 0.2. And we can do the same for our base numbers. So we can say 0.1 plus 0.2. You may have seen this in something like Python before. HScript operates with a very similar syntax. And we'll see repeatedly throughout these lessons various mathematical operations that we can perform. So for example, 0.1 plus 0.2, or we could have 0.1 minus 0.2, which is minus 0.1. We can do multiplication and see the result there, 0.02, when we multiply these two numbers together. And we can also divide using a forward slash. So we see 0.5 in here because we are dividing 0.1 by 0.2. And we can change these values out here. So we could say 5 divided by 2, and then we swap in these numbers for foo and bar. And we would see here that 2.5 is the number that we get as a result out of this here. So we can use numbers and variables interchangeably. So we can say foo divided by 0.1 would be 50 because we are dividing 5 by 0.1. And it doesn't matter what combination of variables and numbers you use together, you can always generally imagine the outcome if you know these numbers in advance. So now that we've got that out of the way, what happens if we have some complex functionality that we want to perform inside of Houdini repetitively? Well, there is a syntax for that, and that syntax lies as knowledge within the repository in Vex for all Vex functions. So before I go anywhere with functions, I just actually want to open up the help menu by just pressing this question mark up here that says click for help on our attribute wrangle. We can actually see in here that we've got quite a lot of good information about the wrangle itself, but not a whole lot of knowledge on the Vex language. So once we're in the attribute wrangle help context, we could just say Vex language here. And we get a little bit of an overview of everything that's going on in here. So this overview of Vex is quite useful to us, and we're going to rely on this quite a few times throughout this course. One of the reasons that Vex is such a joy to learn is because everything is explained to you. Maybe not the reasons as to why you should use something or necessarily the underlying functionality of these things, but you will get a very literal description of what it is you're doing through these kinds of help documentation menus. And you can see here, we've got a variety of scenarios that we can rely on if we want some additional references for what it is we're doing. But the thing that we're going to be using the most out of all of this is the list of functions that we want to iterate over, and also the Vex language reference. So if we scroll down to the bottom down here, we can see this list here, Vex functions. If we just click into this, we can see here there's an absolutely massive list of functions. I mean, thousands of functions. All of these have their own syntax in terms of what parameters you can provide to these, in the same way that there are thousands of nodes in Houdini that you can have additional functionality. So we can actually search in here by filtering these out. And in doing so, we can create for us a list of things that are relevant to what it is we might be doing, for example. So if we typed in array, we can see various functions with the name array in them. So if these like insert will have functionality that is relevant to an array. And we can also see here that some of these functions have actually been grouped by the context in which you may want to use them. So for example, strings, you've got find, USD has its own set of functions, and arrays will have their own set of default functions as well. So the first thing that I actually want to do inside of Vex is just go over some of the really basic functions, things that we can totally imagine ourselves using from the get-go. Something really simple might literally be something like rounding a float to an integer. So we already know that if we were to say, for example, take our float and it was 5.54, and if we turned that into an int, it would actually be returned to us as a rounded number. So if we were to say here, int foo equals 5.54, and f at example, which is a float point attribute, is foo, we'll get this warning like we did in our last lesson, and we'll see that here it's now 5. We would say 5.8, it hasn't changed from being 5. And if we were then to say 4.8, it's now 4. So it's rounding down in this instance. But what if we want to just say, let's round this to the nearest number? We don't want it to round down explicitly because this is quite unpredictable functionality. So what we actually want to do is have a little bit more control over the way that this rounds. So we can go in here. We have a rint math operation. If we just click on that, we have a whole lot of other functions that are related to this as well. When we go through into this function, we have things such as ceil, which will take us to the greater rounded number in a fractional. So 4.8 would always become 5, 4.2 would become 5, etc. We just have frac, which will return to us only the decimal point after 4. So we have loads of functions that remove the need to create this functionality within Vex. So what does all of this mean? Rint Vex function rounds the number to the closest whole number. How do we use this in context of Vex? Most functions aren't going to come with an example for us to use. The only ones that are going to come with an example for us to use are going to be very, very complex functions. Functions that actually probably require quite an advanced level of Vex knowledge when going into them and using them. So in this instance, we have 2 different lines here. This essentially means that there are 2 different data types of which we can use this function for. And this is important because each function is going to have data types that is specific for, and you might find that you can use them across multiple data types, but this is always going to be explicitly defined here. So we can see here, one function returns a float and takes a float as an input. What exactly does all of this mean? This essentially means that when we use the function rint, we need to provide it a variable or a number. In this case, this is going to be our foo. And it's going to return to us a float. This is good because we know what to type in this instance. So we need to type rint with these brackets. We know what's going to go in here. It's going to be a float. And we know what's going to come out. It's going to be a float. So let's just try this really quickly. We can say float foo equals 4.873. When that is returned to us through our geometry spreadsheet, we actually get 4.873. But we're not doing anything to say that this is explicitly rounded. There is no integer component to this. We essentially want to say, what is this number? It's 4.873. And round it to the closest whole number. We don't want to do anything such as creating an integer from this because we know from before that this is just going to round it down even though it should be rounding up. How do we type this out? We have to type this out in the same way that we see it here, but minus this, because this is just telling us what goes in here. So we would type it out as such. F at example, which is creating a floating point attribute called example, is equal to rint. So this is saying this attribute is going to be the number resulting from this operation. And we can type in RINT and then open our first round bracket. And we can actually see here that the exact description for what's going on in our help function is given to us here in the attribute wrangle when we type in this open round bracket. Rounds the number to the closest whole number. Tells us the same thing as what's going on in here. It tells us, same again, float rint, float n. We're going to have to kind of use our imagination a little bit as to how exactly this is going to work, because we're not going to need to type in this float and we're not going to need to type in this float. All we want to do is just say rint and then put our variable name in here where n would be, and then close this up with the bracket. And then not forgetting to close this instruction off with our semicolon. So we're going to say here rint foo is our input into this function, and then close that with a semicolon. And then we have it. We have 5 returned to us. This function has hidden away some code that is performing a mathematical operation of rounding this to the closest number. What you're essentially going to find here is that complex functionality has been optimized and written by side effects in a way that gives us a very efficient and purposeful way of rounding a number upward or downward from whatever it's closest to. So for example, we said 1, 5, it's not going to give us 4. We get 5, 5, 5, it's going to give us 5. Whereas if we were to say, for example, create another float, or it's actually an integer, bar equals 4.55, and then say FXTD bad equals bar, we can see here that the functionality that we wanted from this original function is not only giving us a warning, but is also a different value, because this function has been passed through it with the explicit purpose of rounding to the closest whole number, not the lowest whole number. We can also perform the same functionality with any variety of these mathematical functions in the same way. So just to recap over this again, we have a number that we want to round to the closest whole number, and we want to say we round that number up to the closest whole number by using the rint function. So we cast it to an attribute by saying f@example. So float point attribute example is the resulting value of rint foo. And the functions that are default to Houdini will always be in this turquoise color here. So you'll know you've written it correctly if it comes out in this turquoise color. And this is only for default functions inside of Houdini that side effects have provided. So there we have it. We've written our first resulting function in an attribute here. We can do the same thing if we just want to type in a number in here directly. We can also do that as well. We can say 9.99 would be 10 and 9.1 would be 9. So we're learning new ways of adding functions into our code to give us a result that we are happy with. Let's say, for example, we wanted to try a slightly more complicated function, such as average. Some of our use cases actually become quite lengthy because there are so many different ways in which we could use a function such as average. And we see it's just typed by AVG. So the name of the function as we would type it in Vex is going to be the same in the help documentation up here as it would be when we type it in our wrangle. And it is described to us as returning the average value of the inputs. So we can see here there are these two first use cases where we just have an integer version of this, where we could type in an integer here, and a float version of this where we could type in a single float. This isn't really going to do anything for us because averaging one number will just return to us the same number that we already had. So we have to use our wits a little bit when looking through some of these documentation uses, because these will just be here because you're allowed to do this, not necessarily because it actually does anything. So just keep this in mind when we're doing this. And when we come down here, this is what we actually want. You know, it's even said to us here. I mean, we've got float average A, and it just says returns A. It's not going to even attempt to make any mathematical operation on this. So pay attention to these, and you'll get a good description of what's happening in a function when you type it out. So we have down here float average, and then it opens up the round bracket and says A colon B colon ... This ... essentially means that when we have a series of parameters on our function, we can write as many of these parameters as we want, and it will continue to perform an operation on the subsequent amount of variables that we add into our function. So we can make our bar variable again. And we can start over again here by just deleting this again and just once again just saying f at average foobar equals avg. And once again, we get everything we need to know about all of this in here. And we can see here, float, avg, float a, float b. All we have to do is just type in our foo and then separate it by a comma in the same way as it appears in the documentation. So foo and bar. And we actually get the average value in between these two. And whilst we could add these together and divide them by 2 and get the same functionality. So for example, if we wanted to say, foo plus bar divided by 2 and we would get the same value, this is abstracted away behind this function called avg. So just to reiterate exactly what's going on here, this here is known as our return type. This is the type of data that it is going to be returned as. So when we have a float here and we're putting in 2 floats subsequently into this average function, we are always going to get a float back from us. The body of the function is the code that is taking place within this function. And we declare exactly what function we are performing on these parameters and inputs by specifying the name of the function in the same way we might do a variable, but then opening up the name with these rounded brackets. And there we have it. We have the ability to now take functions and do multiple things with them. We could even nest another function inside this input parameter here to the function. So we could say rint, which is rounding this here. So the second component of our input is rounded, and it actually changes the outcome of the number in here, but only by very slightly because it's rounding it from 9.83 to 10. We could do the same thing here. We could round both of the numbers in our average and get 7.5 because it is now finding the midpoint between 5 and 10, which would be 7.5. So just an interesting way of being able to take code and do interesting things with it. We can make this perform customizable kinds of functionalities within Vex. So for example, let's say we wanted to convert degrees to radians. We could take the radians Vex function and just search for it in our help page here. And just have a read about what's going on in here. So we know that this converts an argument from degrees into radians. So if we wanted to know exactly how many radians 90 degrees is, we don't have to bring pi into it. We can just say radians, and then the float angle in degrees would be 90 degrees. And then we have this value returned to us. So I'll just call this example. And we now know that 1.5708 radians is exactly 90 degrees because we have a function that performs this for us. And the same thing for the function degrees. Converts the arguments from radians to degrees. And say, for example, we wanted to call this variable our foo and just get rid of all of these. And then float bar equals degrees foo. F example is bar. What we're essentially doing here is doing a round trip back to our 90. So we're saying our 1.5 whatever radians is stored here in foo as a part of converting it to radians from the floating point number 90. And then using this new value of radians stored in foo, we then use the degrees function to convert from radians to degrees and get ourselves all the way back to 90. So really useful to know how to use functions inside of Vex. I hope this was useful to you in trying to figure out more about the way in which functions work. This is the kind of knowledge that is going to be able to take you very far in creating simple code that does a lot with very little. There are going to be many functions throughout this course that have more than 3, 4, 5 inputs to them, all of which are varying pieces of information that are related back to us inside of Houdini. And a lot of functions will have complicated uses, but one brilliant thing about Houdini is that we're always going to have this documentation here telling us exactly what we need to place inside of these functions and how exactly we use them. In Houdini, you also have the ability to create your own user functions. And this is actually in the Vex language reference page. So if you're a little bit more advanced and you still understand all of this, just the same as the variables lesson, feel free to have a look at the Vex language reference and maybe even have a try at trying to create your own Vex function, but only if you're a little bit more advanced and you want to breeze past the content explored here. Thanks so much. I hope you learned a lot, and I'll see you next time. So in this lesson, we are going to be looking at parameters and bindings, and we're going to find out how exactly those things work in Vex in a moment. But just to recap over what happened in our last lesson, we took a look at the idea that we can wrap up functionality inside of what is known as a function. You may already know all about this, especially if you come from a background of programming in another language, but it's good to just recap in the way that Vex handles functions and also learning a little bit more about the ecosystem in which Vex lives within. So figuring out ways of using the documentation and features of the attribute wrangle to help us learn more about different features of Vex and also the full lowdown as to how exactly functions work. So through the way in which we were looking at our help documentation, we found out that radians, for example, returns a float to us, and we could store that in our variable foo. And another thing as well is that those who don't know what functions are, we found out that we can wrap up functionality in code. So for example, instead of saying 90 times pi divided by 180, we can just wrap up this functionality by saying radians, open bracket, close bracket, with a 90 in the middle, and it gives us the same thing. So we don't have to use all of our brain power every time we want to do functionality that Vex is already handling for us. We can use functionality through the sheer volume of functions that are available to us in Vex to repeat tasks in a way that wouldn't be frustrating for us to type out every single time. So in this lesson, we're going to just explore a little bit more about some of the features that come with an attribute wrangle that allow us to speed up the process of writing code and allow us to access attributes off of the wrangle itself. So you may already be aware that we are typing in here f at example equals bar, which is creating an attribute. So we see it here, there's no attribute here, and example appears here. We are creating an attribute in this way. But what you may not know is that simply typing this anywhere inside of the wrangle will actually create this attribute. The reason for this is that this is a binding. This has been bound to our geometry through the code and has been created as it has looked over this code and seen that we have declared that there is an attribute called example. What we can do with this is use this same syntax to load in an attribute. So we could say, for example, if the attribute f at example already existed, we could say float foo equals f at example. And there's no problem with that, even if we don't already have the attribute exist. The reason for this is that when Vex compiles this code, it is going to look at every single declaration of at, and it is going to try and figure out whether or not it exists or not. And if it does not exist, it will just create it so that we don't have to deal with an error. It's sort of a blessing and a curse in the sense that you may enjoy the rigid rules of a statically typed variable, but then also find that you can create attributes from nothing. So for example, if we were to misspell a pre-existing attribute, it would still create it for us. So if I were to put an attribute create down here, and we were to create our example and say it had a value of 5, we just go up here and just make sure that this is working. And we say example has a value of 5, it is a float, it is on our points, and we're still iterating over points here. We can see here that we are actually pulling in this here. So if we were to say f at example b equals foo, we create a copy of the pre-existing values from the points of our original attribute. If we were to say, for example, misspell this, we would create another attribute called example, which defaults itself to 0 because it is being looked over in the code upon generation. And then we create a second attribute from our variable foo that copies over the 0 that is assigned here. So just something to be aware of. But we can, in fact, load in examples as if they were variables in the same way in which we write them. But what do we do with variables that exist no matter what we do? If we put down a box, we're always going to get this p. We can access this p in exactly the same way, but we don't want to put anything in front of it. P, we can see here, is a 3 float, which means it's going to be a standard vector. And it also has in parentheses here pos. P is what is known as a default attribute. It is assumed in Vex that there are several attributes that you're always going to have be the same data type. So a positional coordinate, because we are operating in a 3D software and in a 3D space, it is always assumed that P is going to be a 3 float vector. And for that reason, we don't actually need to specify this F here. So let's say, for example, we want to say vector pos equals P. Instead of assuming it will be a float like we do when we create an unnamed attribute, if we say v at pos equals pos, you'll see that all of our positional attributes have been copied over. It is not assumed that this is a float. So what exactly does this mean? It means that P is always available to us in the geometry context of Vex. Being a default attribute means that whenever P exists here, we can always access its values by just typing P. Generally, your P is always going to be on points. And so for that reason, in order to get this default attribute, we have to make sure we're running over points in order to use at P. It is case sensitive. So if we were to type in P here, we notice that we've created a float attribute here. So same as what we were saying before, anytime you try to initialize a undefined attribute, we are always going to get a float. So if we wanted to make sure that this is actually going to be a P, we initialize it, we make sure it's a vector by saying v at P, but it doesn't exist. So we're going to get zeros returned to us. So it is case sensitive as well. We need to make sure that when we're using a default attribute, at P is going to be capitalized and it's going to return to us exactly the same values that we get from P, X, Y, Z. And then we have pos 0, 1, and 2. The reason why X, Y, and Z appears here and 0, 1, 2 appears here is because we have taken this from a default, which is known to be a positional vector, to a standard vector. And what this essentially means is that without specifically defining what this vector attribute would be in Vex, it does not know what we're going to do with this vector, and therefore it does not register it as a positional vector. But this doesn't actually make any difference to us as and when we're using, defining, or editing this, for example. So another thing we can do actually is if we go back to our scene view, we can actually change the P attribute in the same way in which we define it. If I were to say P at P equals pos, you notice that nothing has changed here. But if I were to say pos times 0.5, it's going to multiply each component of the x, y, and z in the vector of pos by 0.5, and it's going to return to us a half-sized cube. So what's essentially happening here is that we are creating a vector pos from our default attribute P, which is a 3 float on our box, and then multiplying each component of that vector, so the x, y, and z individually, by 0.5. So the size of 0.25 originated from 0.5. So 0.5 minus 0.5, 0.5. That ends up becoming 0.25 minus 0.25 and 0.25. And this change, even though it is a change on the attribute, this changes the position of our box. In the same way that we learned about dot notation, we can actually edit individual components of our P vector. So we can say only in Y is this being applied. And I actually have to say pos Y for this one. So if I just redo that, P dot Y equals pos dot Y times 0.5. So what we're essentially saying here is that the Y component of our default attribute position is being multiplied by 0.5 after being cast to our variable pos here. So even though in this piece of code, we're only changing the value of the variable, we're assigning it to the py of our attribute here. And this returns us a shorter version of this box. So if we were to overlay the other box with this, we would see that this has in fact become shorter. Other default attributes that we have access to are attributes such as normal. So if I were to put a normal down on here, and just to keep things clean, I'm just going to say add normals to points. If we were to look at what's going on here, we can see that our point normals are pointing out from each individual point. And we can say n equals 0, 1, 0, and this means it's pointing up in space, and we'll find that all of our normals end up pointing upwards in space. So before, after. Same thing applies here with n, our normal. We do not need to specify that it's a vector, even though we can, just because this is a default attribute and it is assumed that this is going to be something that you work with quite commonly inside of a Vex context. Another vector that we can use as a default is CD. You may have seen this before. This is the color attribute that often appears, and we can assign that. If we just take this normal off so we can see it normally again. And this is going to be an attribute color. You can see 3 float color. Same as before, it's a vector, but it's something that we can change within Vex without having to specifically say that this is in fact a vector. So the default attributes that we're going to be working on mostly throughout this course are going to be CD, which is color, N, which is normal, P, which is position, and lowercase uv, which would be the UV position of each point on here. But we won't go over that in this one because we will be doing work with UVs later on in this course. So other than the default attributes we actually have indexing variables, which are sort of like attributes, and they are identical to attributes in the way in which we access them. But these variables tell us something about the attribute wrangle itself. So indexing variables are known as point number, prim number, number of points, and number of prims. What this is essentially for is for figuring out where in our run over points we exactly are. So if we were to say we have 8 points, at some point in time, this piece of code will run over every single one of these points individually. But how do we know which point that this code would currently be looking over? The way that we do that is with the point number default variable. The same for if we were in primitives, we would say at primnum. And if we wanted to know the exact amount of points, so I point total count, it would be equal to num point. And num point just basically means the number of points on here. So this would be 8. And if we go over to our point total count attribute, it's 8. The reason why variables like these are useful is so that you can actually provide logic inside of your code, which is going to do certain things to certain points. There's going to be many times where you run code and you don't want it to run over every single point. And you're also going to have times where you want the code to behave differently as to where it is along some kind of geometry or structure. So one example of this would be a line. Let's just put down our line like this, and we give it 50 points. You can see there we've got 50 points along here. How would we know how far along our line we currently are if we were writing this in code? Well, one thing we can do is actually create a color, which is our point number divided by the number of points total in this line. You notice here that we actually have a little bit of a problem. These are going to be a little bit stubborn, these default attributes. They're always going to bring themselves in as integers. So if we want to do an operation where a division for it takes place, for example, we're actually going to have to turn these into floats. And we can use the float variable definition as a function as well to tell something to become a float. And there we go. Let me just press D and make this a little bit wider. We've created a line for ourselves that goes from black to white. And this essentially just means that the division into this point number is going to return to us a single floating point value. So if I just called this effort line pos, you go in here, we can actually see that this is creating a 0 to 0.98 value that tells us what division of our point number, our current total number of points would be. So if we just minus this by 1, we would say that at our 49th point, we would be doing 49 divided by 49, which would be 1. And down here at 0, we're dividing by 0, so it's going to be 0. So you can see here we're going from 0 to 1. And we can cast this floating point attribute into our vector color because it's going to apply it to every single channel we have across this vector. So just one of the ways in which we can use point number and number of points. When we're using a kernel language such as Vex, we have to be aware of the idea that we are iterating over every single point, at least when we're in run over points. Obviously, if we were to run over in detail, we would only have this code run once. We wouldn't get anything as a result of that. But inside this run over parameter definition, we are looking at each one of these points individually. And at the time at which we iterate over that point, we have the number of the point available to us, as well as the total number of points overall on this line. Another thing we can do as well is we can actually give a positional y value at the same as our point number. So we could say here p.y equals point number. And now the number of our point becomes the position of this in space. So you see here, it actually goes up to now 49 in height because our smallest py is 0 and our tallest is 49. The same thing would happen again if we were to do our float conversion. If we were to say point number, divide that by the total floating number of points in all of this, and we would have a 0 to 1 range if we just make sure that the total number of points is equal to the highest point number in all of this. We now have, a 0 to 1 range, and any number of sizes that we provide into here is actually going to always return this to 1. So one of the cool things that you can do in Vex is actually create small customizations to positions and geometry that actually might be quite difficult in any other context. There aren't many nodes which immediately come to mind that are going to allow you to normalize the exact positions across a line in a number of points. And this is actually going to be something that we explore quite a lot throughout this course, is the idea that there are very, very small functionalities in Vex that actually provide you a great deal of customizability, especially when creating an effect that somebody's asked you to do that's never really been done very much before. And so within that, we have a very powerful tool at our disposal. We can actually say any number of these points can have any number of functionalities available to them. And without, using crazy for loops with hundreds of SOPs attached to one another, we can create small pieces of code that will do the same thing and actually be quicker to write when we're comfortable with writing Vex. So it's something that's really, really powerful. Another set of default attributes and variables I want to go through are our globals. Globals are variables that are available in any context, whether or not we're iterating over detail mode, vertices, prims. It doesn't matter. We can always access these, and these are going to be our time-related variables. So, for example, if I were to say p.y plus equals, which means we're adding to the current value of p.y as it stands here, at time. And whatever time we are currently at, it's going to add that to y, and it's going to move it up in space. So if we were to just look at this, from our perspective here, we'll just run this. There we go, we're moving up in time. And this is going to be, by default, a floating point attribute. And we can say time times 0.1 and it gets slow. Just cool stuff like that. And we could do the same to our box as well. If we got rid of this functionality that tells our points where to be based off of what point number they are, we could just say, move this box up in time. This is the same as writing time into a center parameter on our box. And it's just one of the interesting ways that we can imagine time as a variable. We can imagine that the value of time can be assigned as a number inside of our code. So if I were to say current time, f at current time equals time, and we iterate over this, we can actually see the current floating point time as it exists as a variable in here. And as we play through the play bar, the position on the play bar is going to match the current time that we see as a variable. And we can use this for all kinds of things. We can use this to push noises. We can use this to change the color of our box. And when we go over loops and conditionals in our next episode, I'll be able to show you how to use things like this to make different decisions and to choose different pieces of code based off of what time or any parameter conditions that sit within our geometry are ready for. We also have frame available to us, which is by default an integer. So if I say I at current time equals frame. My bad, it's actually a float. You say f at current time is the floating point attribute frame, but we don't need this f here. And we can say, just going through this, our frame is returned to us as our variable. The last global that we have related to time actually is static and is not going to change. It's our time increment. And this is a floating point increment that applies to the division in which time is applied. So this is almost like having a frames per second variable. This is whatever 1 divided by the current frames per second would be. So if we were to divide our time by this, we would get the current frame. So this is the same thing as just writing frame. Our time increment represents the increment of time in which a frame is being applied into time. So if we were to say frame times time inc, we would get our current time. We would actually have to minus the frame by 1 in order to get the current time from this. So we're essentially looking at a couple of different ways in which we can visualize time inside of Vex using our global attributes. So interesting stuff to look at. We've looked at all of the different defaults that exist, how we can access them and how we can change them. Although the first set of 4 default attributes are actually going to be the only ones that we can change. As you can imagine, we can't change our point number, our number of points. We can change our number of points with geometry operations by adding points, but that's something we're going to be looking at in another episode. And we're looking at our globals that we can't set as well. So frame, time increment, we can't set these things within Vex because this is specific to our geometry and all of the attributes that we can edit will just be displayed down here. Of course, we could change a existing variable that holds the same value as time. For example, if we wanted to multiply f at current time by 2, we can in fact do that. But we just can't change the current time because that is a global to the entire scene. And that would probably break lots of things. So we've learned about the dot notation for defaults. We've learned about the various defaults that we can access. There's also a syntax for accessing other geometries that we bring in. So let's say we have a box and we have another attribute wrangle and we want to create a new attribute called f at second example equals 5. Actually, let's use one of our globals. We can use point number. So now we have a number ranging from 0 to 7 on our box, and we want to access it here through the second input on our attribute wrangle. How would we copy this from one to another? Well, we could actually say f at second example and create a new attribute here, but this doesn't do anything. This gives us 0 across the board because we would actually need to type in the same code that exists here on here. But another way that we can access it is also by saying f at second example equals op input 1 underscore and then the name of the attribute that you want to assign. So you can say op input 1 second example. And now we have the name of our attribute here and the value from our second attribute wrangle over here as a second input taken into here. So we're not creating this attribute along this line here, we're converting it over pulling it in from our second input. And if we were to try and do OP input 2, it wouldn't work the same way because we are looking at OP input 1, which is this one here. Same if we were to type OP input 0, 0 once again, because we're just looking at ourselves. So we can also use functions to actually achieve this same functionality. We've learned a little bit about our default attributes, but now it's time to see how they actually work with some of the functions that exist in Vex. So we can access this data by just saying point. And if we look at what's read here, we say point reads a point attribute value from a geometry. So this can be any type. Its usages specify that it could be a float, vector, anything. And all we have to do is type point, open round bracket, a geometry, which will, in our case, be an integer number. We'll read that a little bit more down here. String attribute name, which is going to be text that we have to wrap in quotation marks, and our integer point number, which we know that we can access by saying @ptnum. So we have a description of each one of these in here. So geometry is in these kind of angled brackets that basically tell us that this is a sort of abstract that goes beyond the standard data types that exist in Houdini, and this is more to tell the wrangle something. So when running in the context of a node, such as a wrangle SOP, this argument can be an integer representing the input number, starting at 0 to read the geometry from. So we know that 0 is going to be our first input, 1 is going to be our second, 2 is going to be our third, and 3 is going to be our fourth because of the way that we count up in programming. Alternatively, the argument can be a string specifying a geometry file to read from. When running inside of Houdini, this can be an OP path to SOP reference. Now, we're not going to actually use this at any point in the course because it's quite rare to have a geometry with something that we want to look up, but from another file or from a SOP reference, because it's just generally good practice to bring this into the wrangle so that it makes it more visible for people to see exactly what it is you're doing. So what we're going to do here is actually just run this across the geometry number so that we know that it starts at 0. So 0 is going to be our first input. That means that 1 is going to be our second input, and we're going to want to type in 1 up here. The attribute name, the name of the attribute or intrinsic to read. So this is going to be the string at which we type it in and the name of the attribute. We can read this just by middle mousing our attribute wrangle to see exactly what that would be. Point number, the point number to read the attribute on, and this is going to be the value of the given attribute on a given point number, or 0 if the attribute and point do not exist. So we know that we're going to get returned 0. We're going to get returned the float 0 if this attribute does not exist. So we can just actually try that out really quickly. We can type in 1 example and then @ptnum. And we can see here that we do in fact get 0 because the attribute example does not exist here. It's named second example. So we can just go in here and type in second and then our underscore. And what we essentially have here is our geometry, which is our second input. Our second example name, if we type in, is a second example. We can see that this is a float. So we know we're going to get a float out of this. And @ptnum. Now, an interesting thing about functions in Vex is that we don't actually know in advance what the value returned out of a function like point is going to be in the same way that we do in a language maybe such as Python. So what we need to do here is actually tell that this is going to be a float. We're already doing this here inside of our attribute binding, but we're just going to say here float foo equals point second example @ptnum. And then I'm just going to say f at second example equals foo. And there we have it. We have 0, 1, 2, 3, 4, 5, 6, 7, and the same on this geometry over here. And we've used a function to say, look at this attribute on this input at this point number. And because they share the same point number and point sort, it's the same. If we were to change the sort of the other wrangle and we were to look at this, oh, sorry, what we need to do is actually put this sort afterwards. If we reverse this point sort, we'll see that because the point number that we're accessing, we are accessing it by the literal point number of the input. Changing the point sort of the incoming set of points will actually be changing the values in which we read from this function. So here we can see point number is what we're looking for. And because we've reversed this point, 7 is going to be looking at 0 and 0 is going to be looking at 7. So just delete that sort. Another good way of understanding this is by adding a +1. We can look at the next point that we're going to be looking at. So instead of looking at 1, if we were currently on the point number 0, we'll be looking at 1, 1 will be looking at 2, 2 will be looking at 3. And we'll notice that this shifts it forward actually. 0 is now looking at 1, 1 is now looking at 2, 2 is looking at 3, and 7 is going to return us a 0 because there is no 9th point on this. So just some cool stuff you can do with these functions. Another thing that we can do is we can also use the set point attrib function. So if we don't want to do this binding in the same way, we can say set point attrib. Open this up, and we have a lot of information about this here. But all we really need to know is that we can set a point attribute in a geometry in the same way that we've done this. And all we have to do is just type in the the 0, because this is what we're currently looking over. This is ourselves, 0. We can say second example, same as before. The point number, so it's a similar syntax to the point here, but then the value will be foo. And we can see here that if we would just comment this out really quickly, we don't have any attribute. And when it does work, this here is going to return us the value of this. And if you see me do this, this is just me cancelling out this by turning it into a comment. We'll look at what comments are in another video, but it's just a handy way to write non-effective code by just doing 2 lines like this and just writing some comments above it. So we would say assign the attribute from second input geometry. So you can just type in 2 / like this and cancel out any code, or just type in some stuff to tell you what's going on in here. We'll explore best practices for that kind of thing in another lesson. So now that we know a little bit more about how we access attributes, how we get default attributes from our attribute wrangle, such as the number of the point at which we're currently iterating over in our run points, and how we get things such as the maximum number of points or the color or position or UV, for example, we can now actually move on to creating parameters that do this same kind of functionality. So one thing we can actually do is, say, for example, we wanted to create an additional parameter on here. We can go into our parameter interface and just add a float. So I'm just doing this by going in here, clicking this cog, and saying edit parameter interface. And I just want to drag a float up here. And let's just have it above everything else. And let's just call it test parameter. And what's happening here is that we have just created a test parameter with the parameter name test_parameter, and we want to access the value in which we're writing in here. So I'm just going to say f_foo equals ch, and if we look in here, we'll see evaluates a channel or parameter and returns its value. So what this essentially means is, if you're familiar with the kind of OP syntax and typing in paths with strings to operators in Houdini, this is just a way of finding out where something is on a node. And you can see down here we have an example. We can find float tx equals ch obj geo1 box 1 tx 1.5. And what this basically allows us to do is link up a channel with something. We can say this parameter at this point in the scene can be returned to us as a variable. So if I were to say, let's create a null here as well. If I type in ch and then test parameter, we get our value returned to us. And we're going to use this null in a second, bear with me. But when we type in test parameter, the name of our parameter, we get the name of any parameter that's currently sitting on our wrangle here. But if we wanted to do the same for this parameter interface on our null over here, we just add in a float and call this one test parameter as well. Oh, it appears I've added a vector float 2, we just make that a regular float. If I wanted to access this, I would actually have to go all the way down in the scene. So I would have to say obj geo1 null1 and then test parameter. And now we're still pinned on here, just by the way, just so that you're aware. If I were to look at this null and change the value, this path to the value allows us to return the value of this parameter at this current frame and essentially just return that value into a variable. So let's say, for example, we wanted to visualize this. We could say at CD is whatever value we've got on this null. And this will be assigning it to the X, Y, and Z components of our CD. So we can make it black, we can make it white, and the same would apply for our current test parameter on our attribute wrangle. If we just pathed only to this here, all we have to do is type in the parameter name and we get the same return to us. So just some cool stuff that we can do with Vex. We can make this customizable as a sort of UI available to us in Vex. And I'm going to show you a really powerful trick that allows us to get parameters available to us almost instantly when we're creating something. So I'm just going to get rid of this code. I'm going to go in the geometry spreadsheet and I'm going to unpin this sheet. And I'm going to go in the cog and do delete all spare parameters. What I'm going to show you here is a really powerful way in which we can actually create parameters using Vex. So what I'm going to type in here is I'm going to type in float foo equals ch and then an f. And this essentially forces the channel function that we're using here to be a float. And you'll see here all of the uses here are for floats. This f basically means float. And if you look down here, we can see all of the different channels that we can make here. So we can say ch, chs, which would be a string, chi, integer, chv, which would be a vector, so on and so forth. So what I'm doing here is I'm essentially saying chf, and then I'm going to put in the name that I want our parameter to be. So I'm going to call this foo parameter. Now that I've got all of this in here, we're not actually evaluating anything. And if I assign my CD to foo, you'll see here that we have nothing at 0. It's not evaluating anything, so we don't have anything that we can get from this parameter. But if I go over here and I just click create spare parameter for each unique call of ch, I now actually get a parameter created for me. And this will be in a 0 to 1 range, so I can use this in conjunction with many functions that would also have the same. So really useful trick to know. If I wanted to make a vector, I can say vector bar equals chv bar parameter. And when I create that, I get 3 floats available to me. And so knowing our RGB, if I were to make this 1 in R, 0 in green, and 1 in blue, we would get purple. And I can just assign bar to our CD. And in return, we get a purple cube because this is our purple color. So foo being a float is only going to assign the same value to each of our RG and Bs. And bar is something that we can actually edit in here and change as to whatever we want. And we can use this to create ourselves a color visualizer. So cool, useful stuff. The same thing would apply if I were to just say delete all spare parameters. And I would say I example equals chi example int parameter. This I would denote that it's an integer. And if I just go over here and create a spare parameter again, this is going to create a new attribute for me that shares the same value as the parameter that I've created in my attribute wrangle. So we now know how to access a variety of default attributes, globals, and indexing variables. We know how to access some of the functionality that these attributes afford us by using some of the functions such as point and set point attrib that tell us exactly which point we're going to be looking at and how. And we've also learned how to add parameters to our scripts to give us a little bit more functionality as to what values we're inputting on certain variables, because this is much more convenient than just, say, for example, typing 4. If I wanted to change this up and down and see a variety of effects, it's much easier for me to have this CHI example in parameter over here to actually change this value in a more interactive way. So these are all features designed around providing convenience and efficiency and speed for us in Vex. So I hope you found this useful. This might be a little bit to take in. There's a lot of information in here. So feel free to go over this again and just pick out and write down maybe some of the names of these variables and things. But these are all available on the Vex documentation that I mentioned in the last lesson. So feel free to go over that. Maybe do a little bit of homework on the names of these things just to get it settled in. And I'll see you in the next one, where we're going to actually be looking at how to implement logic around these kinds of things. So thanks so much. I'll see you next time. So just to recap, in our last lesson, we looked over parameters and default variables. These were variables accessible in the same way that we would access an attribute, and we were basically just taking a look at all of the default ways in which we could use these. So for example, we didn't have to specify that P for position was a vector, the same for normals and UVs and things similar to that. And we were also taking a look at default attributes such as point number, which told us exactly the number of point at which our code was currently iterating as. And we could assign that as a variable or use it for functions such as the point function, which we also learned about. So useful stuff to know. And if you didn't quite catch on in the last lesson, don't worry, because we are actually going to be using the functionalities of everything we learned about in that last lesson very, very often. Accessing your current code's point number or a geometry attribute such as position is very, very common, especially when you're in this context of Vex. So today we want to explore adding a little bit of complexity to the code that we've been writing so far, because so far we've only been writing 1 or 2 lines at a time. And the reason for this is that we just want to understand the fundamental programming concepts that we are going to use frequently in Vex, so that when we're writing chunks of code, we're not getting lost in exactly what is going on. We want to get through these concepts as seamlessly as possible so that we can begin to understand Vex and how it fits into the way in which we operate in SOPs. So we're going to be looking at loops and conditionals today, and I just want to quickly explain what exactly those things are. So if I were to explain this through the lens of SOPs, and I just get rid of all of this stuff in here, if we put down a switch SOP, which you may be familiar with, and I just add a second geometry in here alongside my box, what we're looking at here as a switch is if we have just these 2 options, it is sort of a conditional. The condition here is essentially whether or not we choose to be on input 1 or input 0. This is the same thing as a conditional in Vex. Instead of having a box and a sphere, we might imagine that we actually have 2 separate variables that we want to choose between to be an attribute. So in this case, our choice is defined by whether or not we're toggling into 0 or 1. And the same can be applied in Vex. When we create an if statement, which is a block of code that specifies one of 2 outcomes or more, we are essentially making a condition in which certain numbers of blocks can be chosen. How does this work exactly? Well, let's create a sort of analog for what's going on in here. And we're actually going to run over details. So we're only going to run through this once. And this also means that when we create an attribute, it's going to be a detail attribute or a global attribute, you might know as. So let's say, for example, we just begin here by creating our float foo equals 1 and our float bar equals 2. And what we want to do here is have a result variable here, which is 0. The idea here is that we have a switch and we have a box and a sphere, and the output of this switch is defined as whether or not we have 0, which is the first choice, and sphere, which is the second choice. This is the same as creating some very simple logic. It is saying, if this is 0, give us the box. If this is 1, give us the sphere. And if we were to imagine that there are only 2 choices out of this instead of the switch which has multiple, or even in the context of the switch, we can still imagine it like this. We can say, if this switch is on 0, give us the box, and anything else will be the sphere. Not the intentional use of the switch, but this is the same way that it works in Vex. So how exactly are we going to choose between 2 things? We're going to need to write an if statement. An if statement, and the idea behind it is that we just specify the word if, and then we have our condition contained inside these 2 round brackets. And what we can essentially say here is the same thing as we're saying on the switch. We could say if 0, and what we're going to have to do here is actually create a new block of code where these curly brackets define the code that takes place afterwards here. So what I'm doing here is I'm just creating 2 curly brackets and pressing enter a couple of times just to step it down. And what this essentially means here is that this block here in of itself is not the instruction. This if here tells us that based on the condition, we are going to execute this piece of code that's just tabbed forward for the sake of being able to read it nicely. All of the code contained within this block here is actually going to be executed based on the condition as to whether or not this returns 1. So if 1 is going to actually return to us whatever executes within here. So let's say, for example, we want to say if 1 I at result equals foo. F at result equals foo, because obviously this is this is a float. And when we go into our geometry spreadsheet and just go across to the detail area, we can see here 1 is returned to us, because if 1, the value of foo is returned through this f at result attribute. Same happens if we change it to any other value. 5 would be returned to us. But if it were not 1 and it were 0 instead, we actually get 0. So nothing happens. All that we know is that this f at result is being created because the attribute wrangle sees it within the code, but no value ever ends up being appended to it. It's not the value of result. Even if we said it was 5, this is not changing anything because it's not linked up with the code in any way. So what's essentially happening here is we are assigning our 3 basic variables, and we're only actually using one of them, our foo, and we're saying if 0, f at result equals foo. If we wanted to make this independent of this if statement, we could say result equals foo, and then f at result equals result. The reason why this is useful is that it gives us a standardized variable that is assigned to a floating point value before the if statement, and it allows us to change the value of variable result based on the condition of the if statement. So we have if 0, result equals foo. So if we change that to 1, we'll get 5. Change that to 0, we will get whatever the value of the variable result is. And what we can say after that is else, and open up another within this if statement here. And what this is essentially saying is, if the condition here is not met, run this block instead. So we can say result equals bar. And now we have 2, because this condition here is not being met. It's not reached 1. And 1 in programming is generally considered to be a true value. So you might see 0 as false. And I can make a comment here just to make it easier. So if true, run this. If false, run this. Actually, move these around the other way. So if this condition is met, run this code. If this condition is not met, run this code. And the code is basically saying replace the value of the variable result with foo, replace the value of the variable result with bar. And the final value that is passed through all of this code is given to this global attribute here, result. And if we change that, it is going to change the value in here. If we want to change this to what we learned in the last lesson, which would be a parameter that we can create using CHI, this would be an integer. And we can call this our switch. This will essentially mean that when it is 0, it is what is known as falsy, which means that if we were to pass it through into a conditional, it would return as a false, which means it would not meet the condition of an if statement. However, anything else, anything above 1, 1 or above will be true. So this condition will be met and it will run this code. So when we're in 0, we're in 2. You can just make sure when you're running this code as well, that you're looking up here just to see what happens to this result. And if it's in 0, it's 2. Anything above, it's 5. And we have the exact same logic implemented here in our switch. 0 will return our cube, and anything above will return our sphere. So same logic being applied here through our geometry spreadsheet. The genius of this is that we can actually apply the logic that goes on inside of these wrangles to things like switches. So we can actually visualize sort of what we are really realistically doing through our switch. So let's say, for example, we wanted to scrap all of this code except for our if-else statement. And we just say here that int true value equals 1, int false value equals, actually we're going to make one of this one 2 and this one 1. And I'm going to also have our int result equals 0. And within our if statement, I'm going to say result equals true value. And else, if this condition within the switch is not met, we get a false value. And I'm going to say I switch value equals result. So here we can see we got our switch value as an integer. And if we have a falsy value of 0, we get a 1, and anything else gets a 2. We can actually link this up with our switch. So when I go in my switch over here, I just want to say add spare input. And I'm going to go over to this open floating operator chooser. I'm going to choose my attribute wrangle. And all we have to do is just put in detail -1. I'm just going to check what the name of this is. Switch value. And I think this actually means a 0 at the end. So now our switch is being controlled by our attribute wrangle. We have a global attribute that's outputted from this attribute wrangle, and the condition at which is being met is returned based off of whatever the true value is and the false value is. So right now it is returning 1, which will be our sphere. And if I were to add a third into the mix, which will be R2, we can choose between our torus and our sphere. And if we get a box, it essentially means that our code isn't working. So I'm just going to put a color in here to make that red, just so that we know that it really shouldn't ever be this box. And this is how you'll know that the code that you've worked out is returning an attribute or isn't returning an attribute. It will show this box. So just to recap, we've got a true value, a false value, a result integer, an if-else statement with a switch that determines which one of these code blocks is actually going to run, and then a final value attribute global, which is given the value of the variable result. And this can either be 0, which is our bad box, means we haven't done this correctly, our true value, which is good, torus, and our false value, which is good, which is our sphere. And now if I choose between these two, you can see we have the same implementation of our switch with the additional factor of if we deleted our if statement here, we get our bad box. So very, very useful, very useful. It's this kind of logic that we can implement to ensure that we have a series of complex conditionals that tell us exactly what is happening within our code. And you can imagine that a switch is a very similar thing to an if statement. An if statement is just looking for a condition to be met here. And then anything else, it is going to run this. So you can make a very specific condition here, and maybe most of the time it will run this else code. Or you can run a condition based off of a point number. So let me show you how that would work really quickly. I'm just going to get rid of all of this because we don't need this anymore. And I'm just going to put down a sphere. Let's have a look at our point numbers over here. And I just want to choose a point number that I want to single out in our if statement. We can obviously do this with groups using a variety of SOPs, but this is just an interesting way of introducing the concept of an if statement. I'm going to put an attribute wrangle down, and I'm going to say in here, if ptnum, which is our default point number of the point at which we're running over in this kernel, if I say if ptnum is equals, and this operator here essentially just means equal to. So this is the same as like running an addition or a multiplier. It is essentially taking two numbers side by side, and the condition as to whether or not it's been met will return a 0 or a 1. So this basically means the current point number that we're looking at equal to the following number that's going to come after this. So we're going to say, is ptnum equal to, so look at 73. And we have a piece of code that runs. We can say our color will be the vector red, just using that syntax for creating a vector with the curly braces and commas. And we can see here that we've given ourselves a point color of red, and it only applies to this point number 73. We can also say else and open up that code block again with two curly braces and say at cd equals 0, 1, 0, which would be green. So if the point number is 73, put some red on that point number, and anything else could be green. We can also actually utilize something known as an else if statement. So we can say else if, actually let me just get rid of this else in here, else if, and you type it just like this, two words separated by a space, else if, lowercase. And we can also add a conditional in here with two round brackets. ptnum is equal to 74. We can give some other kind of code in here. So 74 is down here. cd equals 0, 0, 1, which would be blue. So what we're essentially saying here is there are two conditions that can be met as we go down the chain. There is the idea that a point could be the point number, the point could hold the point number of 73. A point could also adversely hold the point number of 74. And two different pieces of code are run depending on the condition that has been met. So our color could be red if it's 73. Our color could be blue if it's 74. And anything else, the color is going to be green. Useful to know, useful to know. And we can put together other operators other than this equals. If I wanted to go through and type this again, I could say if point number is less than, which is denoted by this less than operator here. If the point number is less than 50, the color is going to be red. And we can see up here, because we have a very nice series of point numbers on our sphere, it gives our sphere a little red hat. We can also say else if point number is greater than, using the opposite facing bracket, 75, make our color blue. And this basically means that these points that are over 75, not including 75 and 74, are all going to be blue. So all the way around here, we can see all of these point numbers. It's actually kind of hard to tell, so let's just make this black. We can see that these point numbers are all greater than 75. So 76 is the first where it begins. Let's say, for example, we wanted to make this perfect and we wanted to have it exactly on 74 and go beyond that. We could, in theory, say 73, and it closes that up. But if we know the number of the place at which we want to end this, and we want to start from there, we can say point number is greater than or equal to 74. And the idea of this operator here with the equal sign after the bracket is that we are not only going above 74, we are also accounting for the idea that it could include 74 as well. So that is part of our conditional now. And we could do the same thing for this, we could say less than or equals to 50. And we see here that our 50 is now included as part of all of this. And we can still include our else statement after all of this and say 1, 0, 0. Oh, actually, no, let's make this green. We can say else color is going to be 0, 1, 0. So it still works with these complex conditionals. We can give an array of conditions to be set based off of the point number. And we can use these conditionals to implement complex logic based off of specifics of point numbers that would be quite hard to do in SOPs already. So that's a conditional. That's how to handle all of this. We don't just have to make things equal to or greater than or just use integers. It's merely the fact that the resulting input of our conditional must be an integer. So we can actually make these operators work outside of a conditional. So we can say I at is over 50 is equal to at ptnum over 50. And the way that this essentially works is we have an attribute here that's an integer, and we are saying the name of this attribute is it over 50? And this value of this attribute is equal to this operator here. So this is what I mean when I say that this is the same thing as using a plus sign to add two numbers together or using a multiplier to multiply two numbers. We are essentially saying that the result of this operation here is going to be the value of our attribute. So if we looked at our point attributes, we would see here is over 50, which is lots of zeros all the way down from 0 to 50, 0. It means it's falsy. Above 50 is going to be 1. And we have lots and lots of point numbers that share the value of 1 because all of these point numbers have been deemed as being truthy, which means that they are above 50. So useful stuff to know, useful stuff to know. We can do things with our position, we can do it with color. So how would using something like position inside of a conditional work? Let's say, for example, we wanted to know whether or not something was intersecting with the ground, and we wanted to give something a color to say whether or not it was. We could say if, and then just make our if statement like this. We know that the condition we want to give it is going to be the color red, because we want to give everything that's underneath the ground the color red, but there's no conditional in here. What we need to say is we need to use our dot notation for our default p. So we need to say if p.y, which is the y-axis of our positional geometry on our sphere, is less than 0.0, we know it's intersecting below the floor plane, which hypothetically would be 0.0. And we can see here that all of the points that have values in y on their p attribute that are below 0 have been marked with red. So this is just one of the ways in which we can use position as a conditional in here. We can include the ones that have 0 in here as well if we use less than or equals to 0. So it's looking for floating point numbers that are below 0 but not equal to them unless we add this equal sign to our conditional operator. Another thing we can do in here is just do the same thing we did before and say else if, and then add our rounded brackets in here. P.y is greater than 0.25. Our color is going to be blue. Same thing again. Very similar to what we put together before. So what happens if we wanted to say if it's above 0.25 or above 0 but below 0.25? We would actually have to combine these conditionals. And the way in which we do that is we're going to say if p.y is greater than or equal to 0, 0, give our color of blue. This essentially means that everything above is going to be blue, just as we did before. But we actually need to add another operator here, which is going to be our AND operator. So we say that by using two ampersands like this. These two ampersands are going to say that this condition over here is happening, and so is something else over on the other side. So we have two ampersands to say if this condition is being run and the condition next to it is being run, return this value. So we now have two conditions within our conditional of our if statement that need to be met before we execute the code that changes the points color attribute to blue. So what we're going to say here is p.y is less than 0.25. So now we're combining different kinds of conditionals within this if statement. We're saying if this p.y is greater than or equal to 0, it needs to also meet the condition of p.y being less than 2.5. So the height of this being in less than 2.5 units, but above 0 in order to meet this condition to execute the code. This is just one of many ways in which we can put together complex conditions that allow us to define very narrow boundaries for how exactly code runs. If we wanted to say, for example, that there are two conditions that it could meet, so for example, we want a color assigned to everything that's above 2.5 in the positive space, but also include everything that's below 2.5 in here, we could write an if statement that says if py is over 2.5. And then we could also write an else if that says p.y is less than minus 0.25. But if the outcome of both of these is going to be that each time this code runs, we are giving the code that assigns something as blue, this is actually quite wasteful. The reason why this is wasteful is because of a concept in programming that we want to try to avoid as much as possible, which is repetitivity. We don't really want to write the same code twice. CD equals 001 as a vector is fine. It's absolutely fine to write that. The problem here is that we don't want to write it over and over again to meet a certain set of conditions, because we could just go on forever and ever and ever. We could say if p.x is over 0.25 CD, and it would just go on forever and ever and ever, and we would never stop writing conditions in which the code CD equals 001 appears over and over and over again forever. This is very, very wasteful code, and we don't want to be doing this. And in doing this, it makes it less readable and more of a frustration for other people to try and pick up your scene. So we want to avoid this. How are we going to do this? Well, we know we can use an and operator to have it meet multiple conditions, which is not something we can do with an else if statement. So what we're going to have to use is an or operator. What this essentially means is in an if statement, when we write our CD equals 001 in our curly braces and semicolon to end that, when we write our if statement, we are going to have our two conditions. So p.y is over 2.5 and p.y is less than minus 0.25. And in the middle, we're going to put these two upright lines like that. And this means or. This is an or operator. This essentially means that the piece of code that's being executed here is going to return a value, and this piece of code here is going to return a value. And it only needs to be one of these returning truthy in order for this condition to be met. Let's say, for example, we had two variables and one of them was 0 and one of them was 1. If we put both of those variables either side of this or operator, it would always return truthy because only one of those had been met. And whether or not one is met or two have been met, it will still return truthy regardless of what combination of which ones in the or operator have been returned truthy, which allows us to have two separate conditions that are being met simultaneously in the same piece of code. We can do the same thing in here as well, where we say else if p.x is over 0.25 or p.x is under minus 0.25, CD equals 1, 0, 0 for red. And you'll find that it doesn't overwrite these up here because when the condition is met here, it exits the code without needing to come down here. We can add a final else statement in here just to wrap up our learning about conditionals by just saying that anything else will be green. And within this loop, we've managed to make a condition where it can exit early by taking precedence over the other code by being the first conditional that's executed in our if statement. So anything that's over 0.25 in height or less than 0.25 in negative height space, we will give it the color of blue. If this is executed, we exit early and we don't need to continue down this statement. In our else if this condition is not met in the blue, we execute condition for the same, but in the x-axis, not the y-axis. And if you want to brush up on your axes, you can just look at the gnomon down here. And then anything else that these conditions haven't been met in will be returned green. So very useful stuff. I'm sure you can probably imagine all of the different things you could implement with if statements and else if. Very useful stuff to be able to learn and use within the context of an attribute wrangle. So the next thing we're going to be looking at are odd loops. So now we're going to be taking a look at loops. So in computer science, a loop or a for loop is a control flow statement. So if you imagine a flow chart, we have a position in a flow chart that we can actually reiterate back over a select number of statements within our flow chart. And the same thing applies for a for loop in Vex. The idea is that we provide a condition similar to our conditional in our if statement. But instead of returning a piece of code or executing a piece of code based on whether or not the conditional is met, a for loop will continually execute this code until a condition has been met. So where we may run this code if a conditional has been met, the for loop will exit when the condition has been met. So for example, we could have a integer variable known as I typically, and we could add to this integer I variable every time we iterate through a piece of code using a for loop. And we could provide a conditional to this for loop that says, if I has been run through so many times that it reaches this set number that we've assigned to it prior to writing our conditional, exit the loop and we are finished there. And something like that, for example, if our maximum number was 5 and we started at 0 and we were adding 1 every time, we would assume that every time we ran that code, the code would execute 5 times over and over again. The reason why it's good to think of this in terms of a flowchart is because while it is iterating repeatedly, it's doing so in a linear way. So we can run it once and accumulate a number repeatedly. We don't have to think about it in the same way as when we're running code through our wrangle, where it is threaded. There's no threading involved in this. It is just a linear accumulation in a typically written for loop. So what I'm going to do is I'm going to write out a for loop, and I am going to just break down the different pieces of this for loop and how exactly it works. So for example, if I just delete this code, and I'm going to put down the statement for, and this is going to tell us that whatever condition exists within here, we will have a set 3 conditions inside of our for loop. This condition will define the starting variables and the way in which this is ran over continuously within our for loop. So for example, if I say for int I equals 0, and this is our iterable, so this is going to be at the end of this for loop, this is going to be increased by 1 every time we run this for loop throughout this code. We're going to say I is less than 5. So we know this from our if statements. I is less than 5. We know that initially going into this, because I has already been initialized as 0, that the first time we run this, I will indeed not meet the condition to exit the for loop. So I being less than 5 means that if we add 1 to I every time we run through this loop, it will execute a total of 5 loops before it's allowed to exit. So the thing that tells us how exactly we are adding 1 every time per execution to this I, we're going to say I++, which being a C-like language, Vex recognizes that writing I++ will add 1 to I. So all this operator is essentially saying is add 1 to I. So we close this with a round bracket, and we do our curly brackets again like this, and we should see that this is running fine. And what this is essentially doing is running over all of our points. So we have 266 points on this sphere, and each one of these points is running a empty block of code 5 times. So what we can do here is we can actually just create a variable outside of this loop, that's called our int foo, and this is going to be 0. And every time we run through this block, we are going to say foo plus equals 2. So we start off with 0, and every time we run through an execution in this loop, we are going to add 2 to foo. So hopefully, if this is running 5 times overall, we should have 10 returned to us. So we can just verify that really quickly. We can say I at foo equals foo. And if we go in here now, we should see, indeed, we have a resulting attribute value of 10. And because this is running over the current point number, every single point has been given this value of 10. So it is running 5 times per point across 266 points. It can be a little bit confusing to think about, but bear with me and we'll match together in the end. We can change this number to be a parameter, so we can choose the amount of times that this will run. So we can say int num iterations equals chi num iterations, and this is a string in the chi function. We just create a spare parameter by clicking this up here, and we have a parameter returned to us into this variable. We need to just make sure that instead of 5, we are using our variable. So we're going to say num iterations is our variable that this loop limit needs to hit. So we still have it at 5, so it should just run 5 iterations. But you'll notice now that if I change this number, whatever is being put in here is going to be double what's in here, because we're just adding 2 to 0, and then repeatedly adding 2 to that, building an iteration every time. We can make something that squares a number repeatedly as well, so we don't have to have foo plus equals 2. We could start off with the number 2, and we could say foo times equals 2 every time. And we start to get some big numbers very quickly. So if we run it 0 times, we get 2 returned to us because it doesn't run once. If we run it 1 time, we get 4. And if we run it 10 times, we get 2048. So we're squaring this number and it gets very big very quickly. And this is just one of the ways in which we can think about using for loops to iteratively run over a single variable that exists outside of the for loop. And the reason why this needs to exist outside of the for loop is because if we have our int foo equals 2, this variable is never defined outside of this for loop. So within this, we need to understand that anything that is defined inside of here, if I say int foo equals 0, we have to know that whenever we initialize a variable inside of our for loop, it is not being returned to us outside of the for loop. It will error for us anytime we try to use it. So this is a set of functionality that is not going to create variables for us. We don't want to create variables in here unless we are using them as part of the overall logic of our script. What we can do is we can say foo plus equals bar. We can add foo to bar, so we can interact with these variables that we're creating inside of the for loop, but we can't use any of the variables that we create inside of our for loop outside of it. So if we were to say try to access I, once again, we see that this is only available to us in terms of this for loop in here. So we can just put that back to foo. We can, however, use I inside of our for loop. So if I were to say foo plus equals I, every time this iterates over a new iteration, the number I will be added to for loop. So for example, if this is 1, this is going to be 0, because the first iteration is going to be 0. If we add 2, then it's going to be 1. But if we make it 3, it's going to be 3 because it is adding the first number, 0, the second number, 1, and then the third number, 2, which would add up to 3. And this kind of thing is really useful if we want to, say, iteratively run a piece of code on something over and over again. So for example, we want to have a randomized number that is changing every single time we run through this. We can use I as a seed, and we can say use rand, which creates a random number between 0 and 1 from a seed. And we can then make foo a float. and then just say f at flu instead. And every time we iterate through I, we are going to get a different random number. So if we run through this 25 times, we get something that's close to half of 25, but not quite, because it is, of course, randomized. And every single time I is being provided as the seed for rand, which is a different seed every iteration. So every new number that's added to foo is always going to be a unique randomized number. So interesting way of thinking about a for loop is, you've got this component here, we're initializing a variable, and we are saying I needs to progressively gain one number every time the loop is executed. And at the point at which it's gained so many numbers that it is greater than the maximum amount of times we've wanted to iterate through this for loop, we need to exit and then just continue on with the rest of our code. So this is what is meant by a kind of control flow statement. If we imagine this in a flow chart here, this would be at the beginning, this would be a kind of winding iterative part of our flow, and then this would be the output at the end of it. We can actually use all of these statements in combination with one another as well. We can say, for example, if foo is less than 0, and then just press tab to bring this out, and a curly brace at the beginning here, and a second curly brace down here. We can say, if foo is equal to 0, we can say that this would run through this, else foo equals 5. So let's say, for example, we change this initial variable to, say, 3. It would return us 5 no matter what. But if foo was 0, we iteratively add our randomized number to this over and over again. So we can combine and mix and match these kinds of functionalities. Another thing we can do as well is use one of our standardized general attribute variables to add an extra level of randomization to our seed here. So let's just get rid of this if statement and press Shift Tab to bring this back in. I can actually add ptnum, which is our current point number that we are iterating over in this, to give me a randomized value. So some of these numbers will be big, some of them will be smaller, and it all depends on how lucky these numbers get as to how much bigger they actually are. So we can see here one of these numbers has managed, with the set of seeds we have combined here, managed to make its way up to 27.5, whereas down here some of them have been smaller values throughout their iterations as a randomization of both ptnum and I, and they have become 19. And what this essentially means is that now we have not only a way to use our point number as a way to kind of randomize or change the code that is being executed per point, we also have a way to iterate through things in a way that will continue to be non-deterministic throughout every single loop that we're running with our for loop. So for example, if we wanted to say, bring this back down to 3, and we wanted to say p.y is now being added to by foo at the end of this, we now have a moderately randomized set of points that are being iterated over, and all we have to do to just bring this value down is make it maybe a bit smaller, and we get an extended level of functionality depending on the amount of iterations we put in here, as well as the total number that we add in here. So we can kind of average out the randomization by doing something like this. So just an interesting thing to think about, the idea of randomization and the way in which we approach it, not only in an iteratively way, but also across points on our geometry itself. So let's strip this back a little bit. And let's imagine that the float foo is a randomized number based off of our point number. And if we were to just look at this really quickly to just make sure this is working, we can type in f at foo equals foo, and just look at this and just see here that yes, indeed, we have a range of randomized numbers from 0 to 1. We can also solo out a variable if it gets a little bit difficult looking at these, by just typing in the name of the variable up here if we want to take a look at that a little bit more closely. So we've started out here with our randomized number foo. We want to make sure that each of the numbers is getting as close as 1 to possible without approaching over 1. So we want to add repetitively 0.1 to each one of these to make sure that we can get it as close to 1 as possible as it can get by having 0.1 added to it over and over again. And when we find that the number has gotten close enough to 1 and adding 0.1 again will take it over 1, we want to exit the for loop. We can do this quite simply. We can just say for int I equals 0, which is our initialized iterator, and we can say I under num iterations. But this time we are actually going to hit delete all spare parameters using the cog, and I'm going to call this max iterations because it's the maximum amount of times I might want to iterate through this. So we can just, even though our code isn't working, we can still just use the create spare parameters for each unique call of ch button, just to make sure that we've got a maximum number of iterations. So this is the most number of times that this code is going to run. It cannot run more than this. And it's good to add something like this to your for loop so that you can visualize exactly how many times the code within this block is going to run until you want it to just give up and stop continuing. So I'm going to say I++ because that is going to continue our iterator forward until it reaches the max iterations. And I'm going to say foo plus equals 0.1. So we can see here that now that we've added 0.1 many times, some of these numbers have basically reached 1. And if we brought that down to 9, we would see that some of these numbers don't go over 1, which is exactly what we wanted. We wanted to add 0.1 as many times as possible without getting it over 1. But we can see every other number has actually gone above 1, and in some cases with numbers that are already very close to 1 have gone way beyond and are almost at 2. So what we need to do here is combine this with one of our if statements and say if adding this number is going to be more than 1, exit this loop. And we're going to use what's called a break function. So just type in like this. If foo plus 0.1 is over 1.0, we open up our code bracket here, and then just press tab to step this forward just to make it more readable. Sorry, we want to say if foo plus 0.1 is less than 1.0, add this. And this is good. We now have a range of numbers that don't go over 1. We get one number that comes extremely close to 1, but given our amount of iterations, if we increase this to 10, we know that this is the maximum amount of iterations we can basically run before something would go over 1. So we have what is essentially would be our maximum number here, 0.9, because if it added 0.1 to this, it would go over 1. So we've managed to successfully implement this logic, and I can just go over this again for you really quickly. So we start with a randomized number between 0 and 1, and we want to add 0.1 to each iteration through this for loop. So we have this for loop here, and our iterator tells us the amount of times we're going to iterate through this. We have our maximum possible number of iterations, which is 10, and we're adding 1 to this I every time. So the maximum amount of times we can run and execute the code inside of our for loop is going to be 10. We're then checking to see if adding 0.1 to foo would take us over 1.0, but we're not actually casting this to our variable. We're just doing this addition in here and checking it with this conditional. And if the criteria has been met, we can then go ahead and add 0.1. This essentially means that if we were to add 0.1, we would go over 1.0. We don't execute any code. And if foo, for example, is 0.8, and we know that adding 0.1 would make it 0.9, this is going to be less than 1, and essentially means that we can go ahead and execute this piece of code here. So we essentially have two conditions of which to execute code. We have our iterations, which we are repeatedly executing over and over again until we meet our condition. And our second condition here, that the incoming number foo needs to be less than 1. But what happens when we reach that condition very early? For example, some of these numbers, as you can see here, without any additional adding being done, already meet the condition at which they would run through this code 10 times, but none of those loops would the number foo ever have 0.1 added to it. What we can do here is a break. We can say else break. And what this means is we are now optimizing this code fully by saying that if we have found that adding 0.1 will take this over 1.0, exit this loop immediately. And this bypasses our condition and nullifies it in the sense that break will tell our loop that the condition has already been met because we have said break, and we will immediately exit the for loop and continue this code that's being executed down here. So it is an instruction in our control flow that says, if this secondary condition is met, discontinue the for loop. And this is really good because it means that we're not wasting additional CPU time on a function that would be running code but not doing anything. And this is useful for times where you have a goal, such as your maximum number here. And we can actually make this into a float and say goal number, and just add this into here. And our goal number can change based off of this parameter here. And if we have 100 max iterations, if we were to remove this, you might find that the running of this might end up getting quite slow. So we run it 10,000 times, run it 100,000 times, run it 1,000,000 times, and it does get slightly slower every time we say this. Run it 100 million times, and we immediately see here that this condition gives us a very, very, very slow wrangle. And so we're seeing here that it's already taken 13 seconds to iterate through this. And having waited 13 seconds means nothing really, because what it means is that we've done 100 million iterations of our for loop. And this just goes to show you how fast Vex is, where we have code that's not running and we can run it 100 million times. But in doing this, we have wasted 13 seconds because we know that if we had our break function in here, it's instant. There is no additional heads up time. And so instead of waiting 13 seconds now, we just tell our loop to break as soon as we reach our goal number. And having reached our goal number essentially means that we no longer need to continue. So useful stuff to know. Obviously, it's going to be quite rare that we're going to need our max iterations for something like this to be this high. But the reason why this is useful isn't necessarily because you might be running over something per point millions of times, but more the idea that as we learn more about the complexity of Vex that we can add, we can also add functions that perform very, very computationally heavy functionality, especially where geometry is concerned, or maybe geometry groups. And what this essentially means is that we can quit at a point at which we know we have done exactly what we set out to do when planning out our functionality in Vex. This means that time will be saved, and we will overall have a much friendlier user experience when dropping this code down onto something else, because it means that there is no unnecessary wait time when using a condition such as break. So for my final example, what I'm going to run through you with is this idea that we can apply choice through our randomization and run that through iteratively using a for loop multiple times, and then have a third condition where this will break that is not dependent on our logical choice, and then visualize that through our color. So what we're going to start off with is a blank color. It's going to be 0 in all axes, which is going to be black. And then what we're going to do is we're going to keep our max iterations, and we are going to use a seed that we generate in the same way as we did before, using a randomized value from our point number and I, but we're also going to introduce a variable parameter seed number to that. And then anything that's under 0.5 is going to have a little bit of red added to it, and anything that is over 0.5 is going to have a little bit of blue added to it. And we should hopefully see the variation in randomization after all of this, once we visualize this on our attribute wrangle. And in order to prevent values from going over 1 prematurely, we are just going to add a small condition that says apply this break to our for loop if we get over a total vector length of 1. So this should be an interesting thing to see if we can do. So let's just put down another attribute wrangle. And within this attribute wrangle, I'm just going to do the same thing again. I'm going to say our max iterations is an integer and also an integer parameter called max iterations. And this is going to be created as a parameter using this here, create spare parameters. And we are just going to give this a maximum number of 100. Just because we know that this can run many, many times, and because we're going to add a break condition to this, we want to know that we can run it as many times as we possibly can before it ends just on its own accord. We're going to start with our blank color, and it's going to be called vector col. And we can just give this a value of 0 in all axes. Using a for loop, what we're going to do here is we are just going to say for, open up our round bracket, int I equals 0, I is less than max iterations, which is our condition, and then I++, which is going to add 1 to our iterator every single time. And we're going to start this off by getting our randomized number. So I'm going to call this choice because this is going to be the decision-making logic and the seeded randomization that we use to determine our logical choice. So I'm just going to call this float choice equals rand ptnum times I. But from what we know here, we can actually assume that a lot of these randomizations are going to clash because the numbers in this sphere are quite small. And so we might actually end up with a lot of seeds that end up being the same. So everything times 0 is obviously going to be 0. So we know that all of our first iterations are going to be the same thing. So what we actually want to do is add another seed into the mix. So what I'm going to do here is I'm just going to say int seed equals chi seed. And this can be a number that gives us a variety of looks based on a parameter that we've created. This adds another additional layer of randomization to this. So instead of this being ptnum times I, I'm going to say ptnum times seed plus I. And this is going to give us a higher degree of randomization between our iterations and also our points. So now we need to add in our conditional. And we already know how to do this. We can just say if with a round bracket, and we can say choice is less than 0.5. So because our randomized number is going to come out as 0.5 on average, because it's a number always between 0 and 1, the best midpoint I can think of to add here is 0.5. So scattered across thousands or millions of iterations, it should average out somewhere around 0.5 because it can be any number between 0 and 1. And I'm going to say if it's less than 0.5, we're going to add a little bit to the red. And then conversely, anything else, which will be above 0.5, a little bit of blue will be added to this number. And now we have a series of choices through our max iterations that should return us a color. We haven't added a break condition yet. So in theory, this should be a number that doesn't necessarily return us anything underneath 1 that would be visible in a convenient way for us. So just gonna set this to 10. And sorry, I just realized that we are actually only adding 0.1 through this blank piece of code here. So this is just another example of how sometimes things can get a little bit tricky and confusing. We're just doing add 0.1 here, but we're not assigning this to anything. So in order to make sure that we're actually assigning this to the variable, we need to say plus equals 0.1. So that is just going to continually add over the top of these dot noted components of the vector color. So here we have many iterations where we see that eventually over enough time, we just make everything pink. And we don't want to do that. We want to make our break condition. So how do we know whether or not the total sum of this vector is going to reach a length of 1? We can actually use the length function. And we can say if length, and we can see here, returns the magnitude of a vector To get the length of a string, use len. And all we have to do here, we know it returns a float. So we have to compare it to a float. So we're going to say float length and then vector v. So all we have to do is just provide our color. We say length color is over 1, which would mean that the brightness of this is going to be over 1. Break. And we can actually add an equal in there because we want it to be equal to, if it ever gets equal to 1.0, sorry, we want this to exit out. So now we have a version of this that is going to give us a randomized set of components that are added upon one another that can either be adding red 0.1 or blue 0.1. So within this, let's just do a quick recap of what we've done here. We've set our max iterations parameter. We've created a seed at which we can change the randomization of our future code. We've created initialized a blank color vector. And we are using this for loop to iterate over the amount of iterations of code within this block here under 100 times. And we are adding 1 to our iterator every time. But we never quite reach that 100 because when we generate our randomized number here and we add 0.1 to our color based off of whether or not our randomization is less than 0.5 every time, we are checking to see whether or not the total length or brightness of our color is going to be over or equal to 1. And if it is, then we exit this for loop. After having exited the for loop, we then just take our color attribute and just assign this variable col here to it, and that gives us our resulting color. If we want to spice this up and add a little bit of customization in here, we can say 0.33 and then else if choice is over 0.33 and less than 0.66, we can add a bit of green in there. Sorry, choice is 0.66. So what we're doing here is we're just saying else if, and we know that anything under 0.33 is going to be under the first third of possible values for our randomized float choice. And then if it is over 0.33, it could also be blue, or it could also be this new middle number that we've chosen. We've chosen 0.33 because it is a third of what it could be. So we're also saying here, and compare it to this conditional. So both of these conditions need to be met before it uses the green value. And we're saying here that anything both less than 0.66 and also over 0.33 will be assigned the color of green. And then anything else, it will obviously be over 0.66. So that will be our third component, the blue. And now we get that kind of noisy value that we might see traditionally from vector noises. And we can see here that based upon our seed, we can add a really massive seed here for that extra randomization. And we can see here that we get some areas of red, some areas of green, and some areas of blue, and also many places where these colors have been combined. And because this can run 100 times before the length of this vector is found, some of these vectors will be very lucky in that they could have found the maximum value of red very quickly. But others will have found green very quickly. Others might not have found any green at all. So just an interesting way to imagine how we can use this. And if we were to use it at smaller values, it wouldn't reach enough soon enough. And we can see here that that magnitude comparison is causing some of those colors that never quite manage to get all three in one component. They lag behind everything else. And if we were to add 50 to this, we can see that it makes no change. And everything above that doesn't make any change because within 100 iterations, something has to reach 1 or a magnitude of 1 in order to exit out of here. So we never really get to see any iterations of this over that value. And if we were to remove this break, we would see massively high values that look like white. So we know that break is doing something just by virtue of having this code in here. So we did get a little bit complex in the end. Feel free to run over this content as many times as you need to. And also there are some basic syntactical instructions on the side effects website that tell us a little bit more about how these for loops and conditionals work. But please let me know if you found this difficult and I'd be happy to walk you through it. And in our next lesson, we are going to be recapping over the things we've learned in this first one, because this is a tricky kind of start to Vex. It's always difficult learning a new programming language for the first time. And so what I really want to do in the next lesson is just go over everything in a way that kind of solidifies all of this knowledge, and so that we can continue and then eventually make some really cool projects. So thanks so much. See you next time. So in this lesson, we are basically just going to round off everything that we've learned so far. So we've made it through this week and we have learned an awful lot. There's a lot to take in, there's a lot to think about, and we've gone through a couple of examples that actually have managed to become quite complicated. You know, writing something like this, that like we did in the last lesson, is something that you're not necessarily going to need to come across very often, but we are doing this with the intention of kind of building up our knowledge of the different features of Vex, rather than providing you with a best practice for how exactly we go about and write Vex. So what I wanted to do in this lesson, recap key concepts that we've learned about, things such as data types, operators, functions and contexts, and just talk about those in context of how we write our code. The importance of writing a script with a clear enough intention that you know exactly how you're going to approach something. So for example, knowing how to outline the steps in which you are going to write a script. I'm going to talk a little bit about a concept of pseudocode and commenting. We explored commenting very briefly in another one of the lessons, but in this lesson, I really want to go over how exactly we do it, why we do it, and best cases for when to use it or how to write it. I just want to talk about naming conventions and how to maintain consistently clear and useful syntax when writing code. So this is more about the idea that you may want to return to a script later on at a different point in time, and you may want to explain to yourself how exactly complicated things work. Or even if you're just learning as you go along, which you will be doing, you know, for a very long time. Vex is a massive undertaking for someone, especially that hasn't learned a programming language prior to this. So commenting and giving yourself readability for you to be able to come back to later in the future is going to be a massive boost for your learning. We're going to learn a little bit about efficiency and the limitations of the Vex language, and also a little bit about problem solving. So let's get straight into this. What I want to do before I continue on from here is I'm actually just going to leave this aside for a minute, and I'm going to make a grid. This is good. I'm just going to increase the resolution on this grid a little bit. I'm just going to bring it down to the size, a normal size. Just put this up to 100 rows and columns just to increase that resolution. We can see that resolution by just looking in the wire shaded view, just to make sure that everything that's going on in here is going to be quite high resolution. So what exactly do I mean by writing something with a clear goal or a clear intention? If I were to put down an attribute rank goal, the idea behind this is that we can actually take this and break this down into much simpler steps than it might seem from previous lessons. And while I've been explaining verbally as to how we're going to approach these tasks, this is just because I know in advance as to what it is I'm actually going to be doing. And following along in a tutorial is going to be very different to a scenario in which you have to figure out your own solution in Vex and rely on the knowledge that you presently have in order to overcome something. So, for example, what you may want to do when you're writing out code is just write out an intention. So what I want to do is I want to make waves appear across the length of this grid. And we have 100 points in each direction. We're running over points. And what I essentially want to do is just take a axis in a certain direction and then run a sine function over the top of that to give us waves. So what I really want to do here is figure out the kind of stages in which we are actually going to do that. And this is what it means to write with a clear goal. So I'm going to just at the top here call this our sine wave generator. Actually, I can call this more of like a sine wave morph. And what I want to do after having written this is maybe just think about the stages in which I'm going to take this. So we have this here. We have a couple of attributes that we've learned in previous lessons, such as p, which would be our vector for position. And I just want to make sure that I'm getting that P. So maybe the first thing we can think of doing is get P as variable. You don't have to write out this explicitly when you're a little bit more experienced with Vex. This is just a way of telling yourself exactly what it is you'd want to do, even if you don't necessarily understand how to use it. The next thing we want to do is actually come up with a way in which we can get sign returned from an axis in Vex. So another part of being able to solve problems in Vex is actually by just navigating documentation as we have done and utilizing it as we have done in previous lessons. So what I'm going to do here is I'm just going to go into my help documentation. And I actually just want to find out first if there is a sign function and if we can use sign inside of Vex as we can do in many other programs. So I'm going to type in sign. And as we can see here, we actually have a couple of implementations of sign inside of Houdini. So we've got our expression function here, and we've got our Vex function. This is HScript, so this is for parameters. So what we're going to want to use is this sign Vex function here. So we just click in that. So we have the sign Vex function here, returns the sign of the argument. So we have here the float function sign, takes a float, and we also have a vector sign. And it says here, this is just the same thing as the first function, but each component of our vector has the float format of sign applied to it. So essentially just the same thing here. These two functions do the exact same thing, same functionality. It's just that our component will be broken down into individual floats. So what we're going to want to plug into here, where n is radians, this essentially means that we can apply a constant to our sign function. So if our z, for example, our z axis was being used to plug into this sign function here, the z can extend as far as it wants. It's going to be using the coordinate in z as a radian value to be used in sign here. And it's going to return us a wave along those radians. So because we're giving it a straight line, we're going to get a wave in sign, and we're just going to want to say return sign value of chosen axis. And what this is going to allow us to do is just plan out how exactly we return sign. So now it gives us an opportunity to think, do we want to add in some functionality where we're choosing an axis, or do we want to add in some functionality wherein we just define our axis inside of the sign function? It gives us a little bit of an opportunity as to how we think about this. Then when we have the sign value, apply, I'd say we can say here that it would be either X or Y, because obviously we're on a XZ grid here that's against the floor. So our height is going to be in Y, or sorry, add sign to Y for height. And that is the idea behind writing out our kind of more verbal form of pseudocode. It's about being able to plan out the things that we're going to be doing using comments, typing in these two forward brackets to get non-affecting sentences and characters that don't affect the code. And here we have a very clear idea of exactly what it is we want to do here. We want to take the P, which is our vector position. We want to take an axis from this, return its sign value, and then add the sign to Y for height. So that we know exactly what we're going to be doing here, we can actually keep this in here and write the code underneath it. So I'm going to say vector pos is P, and this is our get P as a variable, so we're getting this as a vector variable here. We can say float height equals sign, and we get the same documentation returned to us here. But now we know this function actually exists in this format, and we can just say pos x. What we want to do then is just add this height value to p.y. So we use our dot notation to separate out the component y in our default attribute p, which is a plus equals, so it's going to add it to py. And there we have this. So actually find that we have a very unusual thing going on at the moment where this is acting very strangely. A bit of problem solving we can do with this before we jump into the specifics of how exactly we're doing this is to maybe try out a couple of things before we go into a code solution. Because until we're very experienced with Vex, it's going to be hard to know exactly what the effects of some of these things are. So what I can do first is maybe just play around with this a little bit and add some size to this grid. We did reduce it down to 1 and 1. I just want to add some size to it. And we can see here, yes, indeed, a value of 10 and 10 is giving us almost 2 waves across the entire surface of this. The reason for this is because this is getting returned to us in radians. Or sorry, taking in radians from our position value. But instead of just saying, using 2 times pi to get us, or using pi to get us a radian or some kind of fractional of a radian in this value, we can actually control the frequency. It doesn't need to strictly be a radian value inside of sine. So what we can do here is we can actually just give it some sort of frequency. We can say times 5 times 15, and now we get multiple waves in our smaller grid. So another thing that we can try as well is just maybe something for like a noise or a sine kind of value. We can try multiplying to see if this changes and affects the way in which the inputs work. So maybe now over here, we can give ourselves a parameter, and we can say float freq equals CHF sine frequency. And we don't need to add a comment for this because this is a very, very apparently clear piece of code for us to have across our code. It's telling us exactly what we need to know about this. We're seeing here that we're getting a float variable that is named freq after frequency. We don't need to know that this is called frequency because we can see over here that our float channel parameter sine frequency is named as such. And all we have to do now is just create a spare parameter for this unique call and put this to a reasonable value, and then just change our 15 out to freq. And now we have a value at which we can change the frequency of how many waves are being affected within this piece of code here. We'll notice now as well, now that we've made our way through this code, we can also see for ourselves that the value in which this is being returned to us is actually quite big. And we can change the amplitude of this as well in the same way. So we can say times 0.5 on the height, and we'll get half of the height that we're being returned to us there. You can say 0.2 and we get a smaller wave. And maybe if we wanted to have a kind of very gradual wave, we would get into very small values that are difficult to kind of keep writing into our code. So we do the same thing again. We can say float amp equals CHF sine amp. You can add that in there and just give this a small value like 0.05. And we can add it in here like this. We can say height is multiplied by amp when it's returned to the y coordinate of our P. So now we have this wave that we can control in multiple dimensions and is written out in such a way that we can quite easily understand what exactly is going on inside of here. And this would be useful if you wanted to make some like quick, corrugated metal or something like that. And this is something that an artist can go in and take a hold of and make changes to as and when they need it. Maybe something that might be a little bit trickier to create in other circumstances. So it's this level of consistency and it's this level of readability that allows us to make code that is easy to hand over onto other people. A philosophy in writing code that I like to follow quite a lot is this idea that the code should speak for itself. And if it cannot do that, then we need a comment. So we can see here, py is getting height added to it. This is sort of self-explanatory here. So we don't need this comment here anymore that says add sine to y for height, because this is more pseudocode for us to plan out this. So I'm just going to get rid of this here. And we'll notice now that just reading this, we can see that our y is being added to by a variable height value that is being multiplied by amp. I don't think this is necessarily complex enough that we would need this repeated to us through a comment. And the same thing here, return the sine value. This is described exactly by what's going on in here. We have a sine function. Maybe if we were writing our own sine function, we would need this comment, but we absolutely do not need this for this. Although the idea that we have a chosen axis of either x and y is still quite interesting. and get p as a variable. Obviously, we don't need this in here anymore, but we can keep this up here because this is a instant descriptor to people coming into the script that might want to know exactly what is going on in here. So if we did want to add a separate axis choice here, we can just say float axis equals pos.x. And the reason why we're using pos instead of just directly accessing p is that this gives us the ability to change this out or make changes to the incoming variable here. And it also means that if we want to add something in here, say for example, we at some point change the p.x, it's not going to affect the overall ability for us to say, for example, have it in the same place. You know, if we were to change this, it actually keeps it in place because it's using p as its position. So the reason why we're using pos is because it gives us a reusable way of being able to access our position. It's generally a good principle to have something like at p cast as a vector if you know you're going to be performing multiple calculations on something like that. So just to get back into this for a second, we did just create our float axis variable. So I'm just going to replace the pos x in sine with axis. So we're just abstracting this out a little bit. Now things like height make a lot of sense to the reader. Height is the sine of our axis position and our frequency. They're very readable, very, very easy to understand. Another thing we can do as well is we can actually just initialize our axis. So just to recap over our previous learning, we could just initialize axis by just having a semicolon here. And we can say if choice axis equals pos x, else axis equals pos z. And this basically just gives us a switch based on the idea that we could then write in a variable choice. So it's like sort of like we're thinking about planning our code in advance of having actually done this. And it's something I like to do is come up with the idea of having written in a variable once I've already written in this conditional. So then it reminds me that I can just go back here and just create an in choice variable and just say that would be 0. So now if we change this, 0 or 1, we get a different axis every time. So I can just say here, chi axis choice. And this just gives us a new parameter for us to change. And we'll notice here that because we have an if else, we are essentially just choosing whether or not it's 0 or 1, but anything above 1 will just end up being brought back to our final choice here. Because anything over 1 is always going to be truthy. Anything under 1 is going to be falsy unless it's a minus value. So we have a clear idea of exactly how we're choosing these parameters, how we make it readable, and how we also make it accessible for other people who want to use something like this. And now we actually have a set of parameters that we can use to change something around and make it more interesting for people to be able to use and interact with. We could also do things like add in a variable t, such as time, and we could increase the amp over time, or we could change the frequency over time. But if we wanted to, say, move this sine wave, we would actually need to offset this. We could do another thing as well. We can say plus in our sine function down here, offset. And once again, we can just underneath our frequency here, just to keep them bundled together. And actually we can move our sine amp up here as well. Let's just move that up there as well. We can say float offset equals CHF sine offset. And now we have another choice as which to add a kind of undulating movement throughout our sine wave. So we could just make this t. And of course, if we wanted to, we could actually just make this time, as we learned from our other lesson, and that would put it directly in on the code. But it's just nice having the ability to give people the choice or chance to make decisions based off of what exactly they want in these parameters themselves without having to go in and change the code. I just moved this around a little bit as well, so we have our parameters bundled up with one another and our initialized variable access down here as well. So now we have quite nicely organized, neatly laid out series of lines of code. These instructions give us the basis for a nice, readable, interactive script that we can reuse again and again in the future. The last thing I'll just do with this script before we move on to a slightly different topic is just the idea that when we do have bundled parameters like this, we can just comment things that describe not exactly what is going on in here, but the purpose of the block of code underneath this. So we can just say here, parameters for sign morphing. You could probably come up with a better idea of what it is this is doing. The words might not exactly always come to you, but just a way of bundling together these kinds of ideas. So this is a good example of how you might want to write something if you know that someone else or yourself is going to be coming back to this and wanting to know exactly how this is going to work in the future. The next thing I want to move on is the idea of when exactly we use Vex and the limitations in which we use it. So I'm going to put down another grid here, and I'm going to put down a blast. Let's say, for example, we want to go through this attribute wrangle and we want to remove every point in here just by using this function here, remove point. We have to understand that every time we call this remove point, it's going to be trying to stack up the different removals of points. We're getting a little bit ahead of ourselves here, obviously, with this function here, so bear with me. We don't necessarily need to know what's happening here. But it's this idea that there are going to be a lot of nodes in Houdini that don't need to be replaced with the same kind of usage of Vex. So if we had millions and millions of points, say for example we had 1 million points here, it's actually, you see a little bit of a stutter in comparison to the blast node here. Same if I had 5,000, 5,000, this blast cooks in about 10 milliseconds. If I go onto this here, we can see it's going slow, very, very, very slow. And the amount of time it takes to actually perform this, in having removed every single one of the 25 million points we have on this grid is orders of magnitude greater than the blast. So it's just a little bit of a warning to over-relying on Vex as well. The philosophy that I like to take whenever I'm writing code, especially in Houdini, is this idea that Vex is almost like a technical last resort or a method of convenience. There are times where we're going to want to wrap up very complex point removal, say, for example, in maybe like a SOP solver where we have a very specific set of criteria that we want to remove a point in that can only be calculated in a wrangle. But we would never just throw down versions of other SOPs just within a wrangle itself. We always want to be able to figure out and identify bottlenecks through our code, and we always want to understand the way in which we approach every problem individually. And that's why Vex is a great tool for building up your problem-solving ability once you get a little bit more comfortable with the syntax of the language. If I were to say pull out the performance monitor that we can see over here, and I were to just go back and give ourselves a very heavy mesh again, I'd say 2000 by 2000. And I would just go on this grid over here, and maybe just actually 2500 by 2500. Big heavy grid. We've got 6 million points on here. Something I like to do, if you just go down into the window and performance monitor, it's down here, so it says Alt-Y as well. I like to be able to see exactly where my bottlenecks are, especially if you're laying down lots of wrangles, or you're laying down a lot of code. You may not already know that this exists inside of Houdini. So all I have to do here is just hit record, and it starts recording a profile of the performance of my scene. So it'll tell me information about the viewport and how much time it spent drawing on the viewport, and it'll tell me here it was waiting on GPU for the majority of the time I was spinning my camera around. So it records literally everything. So if I just go into record and hit record again, if I click on blast, I'll get an immediate understanding of how fast this was. 0.003 seconds to cook this blast SOP. That's how long it took me to delete 6 million points. This is a great way of being able to record how efficient your code is and be able to compare it to how it was previously. So for example, if you wanted to compare various pieces of code that you've written and see how efficient they are, you can use the performance monitor to do that. And I like doing that quite often. There are similar concepts in Python that require you to wrap your code in some kind of timer function where it times the length of time it goes in and comes out at the other side. And this is kind of a similar idea, but with a great visual representation of what's happening here. So 0.003 seconds, and we actually have these recorded in our profiles. I can name this blast SOP1. And then if I just do another recording and name this attrib wrangle 1, and I go over to my attrib wrangle here, we can already get an idea for how much slower it is. But here we go, 3 seconds by comparison. And this is a very small amount of points compared to some simulations you'll see. Some simulations have billions of points. And we can see here that by just iterating over each one, even though we're iterating through them as a kind of threaded environment, because of the limitations of performing especially geometry operations in Vex, we can see here that this is a vastly less efficient operation than our blast SOP. 0.003 seconds here, and we have 3 seconds here. So something to be absolutely aware of when you're writing code is that whilst it is a good learning exercise to be able to write code when you're thinking about learning the language or performing something that can't be found in another SOP, if you're trying to replace functionality from another SOP that already exists, chances are the SOP will be more efficient every time. So interesting stuff to think about. If I just delete these two here as well, another thing we can do inside of Vex is actually get some more visual representations of things that we're looking at on our attribute wrangle outside of needing to cast them as an attribute. It might not always be efficient to create an attribute to visualize something that you're looking at. So where we have our performance monitor to monitor the speed in which our code runs, the last couple of lessons, we've used attributes to get an idea of what numbers are doing and what specific variables are doing at one point in time. But if we don't have the ability afforded to us to create an attribute, or it might be too complicated to create an attribute in the moment, if I just put an attribute wrangle down here, I'll show you exactly what the print functions do. So if I just go into detail mode, which means this is only going to run once, I can show you here that if I say printf, I can say %f, which means that we're going to be printing out a float, and then 0.5 afterwards. And we'll see here, we get a 0.5 printed out for us. So how exactly does this work? Well, let's fall back on our documentation again to figure out exactly what's going on in here. And this is another example of just how fantastic the functionality and level of information you're going to get returned to you outside of the attribute wrangle in the documentation is going to be. It says here we have a C printf format string. When a percentage symbol is found in the string, an argument will be printed out in a format specified by the characters following the percentage sign symbol. The conversion of the argument is specified by a single letter GFSDXCP, and it's actually told to us below exactly what these mean. So in what we're doing in here is we're saying put the percentage sign down, which tells us that the following character is going to be an argument, a variable argument that comes into here, and these format characters tell us what exactly it's going to be. So we can use G, P, or C for these forms, FE or capitalized E for these forms, etc. S for a string, I for these forms, and all of these different forms have different uses inside of C, and that's what makes Vex a more C-like language in its usage. People who are used to seeing these kinds of things in much lower level languages will be familiar with these right away, but this sort of strange arcane form is just something more of a convenience to programmers who already know other languages. But if you're looking to print into the console, some kind of operation. Say, for example, you want to say float result equals 100 times 0.532. We can print out the result. Oh, and if I just clear this here, sorry. We can say 53.2, and then we've got our leading one at the very end there. And this is telling us exactly what our floating point number looks like when represented through a string in the console. We can use a string return character, which will give us a kind of paragraphing, where now if we were to just print that out again, and if I were to say add something in here that would change the result of the code every time, if I say result plus equals chf add, and add this in here, every time I add something, it's going to give me a new line. This is a new line character every time this changes, and we get hundreds and hundreds of values. And if I actually wanted to add something before this %f to say exactly what it is, I could say result colon, and then we get a nicely printed format of this for us. So something different to consider from the standard of just returning result as an attribute wrangle and looking in the geometry spreadsheet to see what it says. We get the longer form floating point number so that we can see if there's any kind of floating point weirdness like these 002s at the end. And we also get the ability to wrap this up in something a little bit more interesting than just seeing it as a number in the spreadsheet here. So these are tools given to you as part of a kind of debugging tool set that allows you to figure out how exactly you're going to approach problem solving, debugging, and code in the future. I really hope this was useful to you. Please let me know if there's anything across the last lessons that may be a little bit confusing, or any of the concepts inside of here that are confusing, and I can explain them in further detail to you. But all of this stuff explained in this lesson is just designed to make the process of writing code easier for yourself, others, and for your future self when you go back in time and you start looking at the stuff you wrote to begin with. Or there's going to be many, many times if you're on your Vex learning journey that you write something that you're actually really impressed with, but then you think about it for days and days and days, come back to it in a couple of months when you've forgotten about it. And now that you've come back to it, you have no idea what it is you've written because you haven't given yourself the ability to write something a little bit more verbose and a little bit more readable. So I hope these lessons kind of help you in your journey of learning a little bit more. And I can't wait to see you for the next week of lessons where we start diving into some interesting use cases and getting into some real complexity behind our code. So really excited for that. Thanks so much, and I'll see you next time.